Okay, so good morning. So today this is the second day and this is the first lecture of second day. So in this we will start with the very basic things about the climate change, and the very second lecture will be taken by Professor Lixin Wang, and in this lecture I will discuss about very basic about climate change, and in the further next lecture we will start with the IPCC. So if we talk about anywhere, either it is a TV or a documentary or a broadcast, or we can say the short-term courses or any conferences, everywhere we are looking at climate change. So the very basic thing is that whether this climate change and global warming are the same or not. This is very basic question. So what do you think about it? These are the same thing, or these are two different things? Whether the global warming and climate change are same or not? What do you think? It is same? No, these are not same. These are two different things. We can say one of the reason to cause the climate change is global warming, but these are not the same. So what is the basic difference between them? So if we talk about the global warming, the gradual increase in the Earth's surface temperature is known as global warming, and whenever we talk about the climate change, we are considering the long-term change in the global weather patterns. So what do you mean by global weather patterns or long-term change? How many minimum number of years we need to consider for long-term? 30 years or more than that? Minimum 30 years we need to do. Even for the downscaling itself, whenever we are doing the statistical downscaling, the minimum number of years to do the downscaling, the minimum means below than that we cannot go is 20 years, and the desirable is 50 years. So if we are talking about the long-term weather pattern or change in the long-term weather pattern, then it is known as a climate change. Otherwise, the simple gradual increase in the Earth's surface temperature is global warming. And even 97% of scientists agrees that climate change is happening across globally. So why this topic is so important for us? Across the global level or across India or any regional level, why we are very afraid about the climate change? What is the importance of this? So if we talk about on a global level, climate change, Henry Paulson, who is a former United States Secretary of the Treasury, he told that climate change is the single biggest risk that exists to the economy today. Second important thing, as per the UN United Emission Gap report in 2019, they told that we are on the brink of missing the opportunity to limit the global warming to 1.5 degree. I think you know what is the limit for global warming we have decided initially. Initially it is decided that we have to limit the temperature increase to 1.5 degree preferably. However, we should not go beyond the 2 degree centigrade, but preferably it should be 1.5 degree. But looking at the current scenario, it is looking like impossible condition for us that we will not limit up to 1.5 degree or 2 degree. If we talk about the Mark Carney, he is a governor of Bank of England. So he also stated a definition or a statement related to climate change, that companies that don't adapt to climate change will go bankrupt without any question. So these are some of the terms related to climate change and why it is important based on the economic purpose or on a global level. But as a researcher, what is the importance of climate change to us? Why we are concerned about the climate change? So there are different risks which are associated with the climate change. If we talk about heat waves, flood, drought, heat waves, cold waves, droughts, flash drought, flash flood, like these are the direct risks which are associated with the climate change. If we talk about the indirect effects, along with the direct effects also there will be some inherent direct effects also associated with this. For example, if drought condition is there, so that will be a problem for us. People will start migrating from that place. Even for the flood condition itself, if it will persist for a longer time, so people start migrating to the another place. Similarly for the heat waves, similarly for the cold waves, due to drought conditions, agriculture production will affect. Due to that also people will start migrating, and due to flood condition, infrastructural damage will be there. So if we talk about direct risk, we have observed a huge change in the temperature rise. Means urban temperature is rising 2.5 to 4 degrees centigrade than the pre-industrial level. I think yesterday itself Dr. Somil has shown that how the temperature condition is changing across before pre-industrialization and after the pre-industrialization period. So you can see that this increase in the temperature in the last 50-60 years is causing a huge impact on the different extreme events. I think you also heard about the urban heat island effect. So it is also one of the effect of the climate change. If we talk about the flood risk, so at various places we are looking at flash flood conditions. Like at Uttarakhand, we have seen the same effect of flash flood. There is a drought risk associated with climate change, due to which we have arable land productivity is going to be reduced in future time. We found that there is a lower crop yield or crop yield reduction in terms of wheat, rice, maize. Why I am saying wheat, rice, maize? Because these are the major crops which we are expecting across the India. So these are some of the 5 critical global environmental changes due to climate, that is warming, increasing temperature, changes in the global water cycle. Due to temperature increase, we are saying that there is a declining in the glaciers or snowpacks, and if these glaciers will start melt, what it will result in? It will result in sea level rise and finally the ocean acidifications. So we are saying that this is a climate change, this is the effect of climate change, this is a direct or indirect effect. But what proof do we have that whether the climate change is happening across globally or across India? So if we talk about the major impacts of climate change across India, these are some of the data set from the WMO from 1970 to 2019 itself. So from here itself you can see that initially, if we talk about the very first figure, the first on the x-axis we are showing the data set for the 10 years. So initially from 1970 to 1980 or 1979, we have number of disaster reported is 711. These are consist of drought, extreme temperature, floods, landslides, storms, wildfires. Out of that, in 1970 we have only 711 events occurring across globally. However, you can see just after 10 years it is becoming the double of the figure, that is 1410 events. In the next 10 years it is increasing to 2250, then it is increasing to 3536, and finally in the next it is 3165 events. So you can see from last 50 years we are increasing from 700 to more than 3500. So this is the impact of climate change, and it is clearly indicating that climate change is happening, and due to which we have number of disasters across globally. Similarly, if we talk about the number of reported deaths, initially you can see this is showing the opposite figures as per the number of reported disaster. Why it is so? If number of disasters are increasing, number of reported deaths should also increase with it. Why it is showing a reduced number? Means initially in 1970 it is 556k, and in last decade it is 185k. Is there any reason behind it? Because due to climate change, disasters are happening, but the government or on a global level we are becoming the resilient to the disasters also. Not in terms of disasters resilient, but also we are giving some facilities so that we can protect our people from the disasters. So that is the reason that deaths are less, but we cannot stop the disasters to happen, but we can take the mitigation or adaptation strategies so that we can save the life. The third important thing which we can see the impact of climate change is economic losses. You can see that initially these figures are in American US dollar in billion terms, and you can see that initially it is 175.4 USD billion, but the same figure is increasing to 289 in the next decade, then 852, then 942, and right now it is 1381. So this is the economic loss we are facing due to climate change across global level. So you can see that we are increasing in the number of reported disaster on every single decade. We are losing lot of economic losses in USD from 1970 to 2019 itself. So this in all we can say that more than 11,000 disasters are reported, out of which 2 million deaths happen and 3.64 US trillion in losses globally in last 50 years. So this is the clear perception that it is showing that we have a proof of the climate change across global level. If we talk about the climate change across India itself, we know that more than 54% of India is facing high to extremely high stress conditions. So mostly these are some of the clips, and I am showing this because we are very vulnerable to temperature condition, we are very vulnerable to flood conditions, we are also vulnerable to the flood heat wave conditions. The most important part of extreme events across India is that, for example, you can see this figure that despite the floods, some parts of Maharashtra are reeling under the drought-like conditions also. It means the same area which is facing the drought in the next coming month, that is the same area is also experiencing the flood conditions, and that is the simultaneous behavior. Means, for example, if you talk about the river basin wise, I think Mahi river basin is that river basin which is experiencing these types of situation, that one of the event is completing, the next opposite one is occurring there itself. For example, you can find the drought simultaneously with the flood conditions at the Mahi river basin. Similarly, there are different areas across India which are facing the same situation, that initially they are facing the drought condition, in the next coming month they are facing the flood condition. So such type of extreme events is very hard to predict, because if you are managing the drought condition, in the next coming month you have to face the flood conditions. So continuously, if drought is there, you can manage the things, you can predict the things, you can do something for that. But if the same event is happening and after that the different one is happening, so it will be very difficult to us to mitigate that thing. Other than that, if we talk about the flood, other than that, if we talk about the glaciers also, because if we talking about climate change, we cannot ignore the glaciers conditions also. So one study happens and it clearly tells that if we are not protecting the climate from the climate change, the Himalayan glaciers will risk losing 75% of their volume by 2100 due to global warming. It means your grandson will not able to see the glaciers. Whatever you are able to see, your grandson will not able to see the glacier. What is that? So you have to show them in the video itself. These are some type of the glaciers we have in 21st century. After that, might be more than 75% of the glaciers will be lost. So if we talk about the India itself, we have different facts about the climate change. If we talk about the flood condition, more than 40 million people were affected by widespread flooding in the Indian subcontinent during different 5 or 6 years as per UN report. If we talk about the drought also, India is one of the most drought prone countries across the world, because we are facing lot of drought events across every single years. If we talk about heat waves also, right now you can feel it, because yesterday we have a very high temperature conditions, and every year from mid-March to May or mid-May to June we have severe heat wave conditions. In the next tomorrow itself I'll take the lecture on heat wave, and we have conducted a heat wave study also. So we will define how we can define the heat wave and severe heat wave, what is the basic difference between them, and how we can define the heat waves, means what are the different conditions to define the heat waves. If we talk about the extreme precipitation, because right now we are if we take a look at the literature, we can see that lot of studies are carrying out for the extreme precipitation. So in the last 65 years, from 1950 to 2015, a study has been carried out by Roxy et al. In 2017, and in their observation they clearly mentioned that in last 65 years the events of extreme precipitation has increased three times. So this is the vulnerability of India in terms of flood, drought, heat wave and climate change. So these are some of the proofs which indicates that okay, climate change is happening across India also. Okay, so what do you think, what is the main reason why this climate change is happening across urban area? Because if you think about that, which one is the more contributing factor to climate change, either rural area or urban area? So urban area is the major contributing to the climate change. For example, if we talk about the expected figures of the climate urbanization in 2050, so after 2050 we will reach that 55% will increase in urban water demand will be expected by 2050. More than 2/3 of the global energy is consumed by the cities only, so that's why they are contributing more to the climate change. If we talk about the greenhouse gas emission, more than 70% of emissions comes from the city itself, not from the rural areas or not from the villages. If we talk about the unmanaged waste, 93% of waste is unmanaged in low income countries. If we talk about the constructions also, more than 0.6 to 1.3 million square kilometer of new built up urban areas are expected to be added in the next 30 years. And if we talk about the urban population, more than 2.5 billion people or more people will be join the cities by the 2050. And if people will join, all the facts which I am discussing will be increased very fastly. For example, if more than 5.5 billion people will add into the city level, urban water demand will also increase, the consumption of energy will also increase, greenhouse gas emission will also increase, and we need to build more construction or more areas. Okay, so this is the 1.5 degree thing which I am discussing earlier, that as per the climate scientists, they have think that 1.5 degree is the level which is associated with the less devastating effect than higher level of global warming. Means they have decided that up to 1.5 degree we can stop the temperature, because up to that the effect of global warming is not very high, it is less devastating. However, after 1.5 degree, this will increase severely and expensive effects of climate change in this. So today we still have the chance to limit the global temperature to 1.5 degree, but by looking at our system or our tradition, whatever we are doing for the climate change, we are one of the contributor to the climate change. So it is very difficult to stop at 1.5 degree, but we can stop it up to 2 degree if we want. So these are some of the climate change issues. Then if there is an issue, we have to solve that issue. There is problem, there should be a solution also. So if this is the problem related to climate change, then what is the solution at a national level or a global level or at a regional level? We have to think about it. So for the climate change, I think there are several association or organization at a global level, And if we talk about it India level, there is a national action plan on a climate change. I think you have heard about this. This is a national action plan on a climate change, which is started in 2008. And the main objective of this is to divide this action plan to the state teams, that is state action plan on climate change. And in each state action plan, they have divided 2 units to take or to collect the data sets related to climate change across the state. The first one is a state action plan on climate change have unit, that is state climate change cell, and second one is a state knowledge center on the climate change. If we talk about this in Madhya Pradesh, this cell is available in the Bhopal only for the Madhya Pradesh state. So these are some of the action plan on climate change, but the problem is that if these are not getting the proper data set, so what is the government purpose, or what is the government behavior, that what they are doing for the climate change? So if we talk about the smart city missions, so smart city mission, what is the main objective of smart city missions? To make the city smart only? Sustainable. Because since we are growing, we are updating ourselves. From bike we are going to the car, from fan or cooler we are going to the AC. So we are updating ourselves. Similarly, along with this, we are causing the climate change. So if we are developing the cities, we must develop the city in the sustainable way. So in this we have sustainable environment, for example renewable source of energies, or if we talk about the urbanized transportation, we must use electric vehicles and all. But in these smart city mission, if you find out the report of 2015 from the MOHU Government of India website, you will see that there are no such plans or policies that is existing for the estimation and mitigation of risk due to extreme events. So we need a plan that can also exist in the smart city, which can estimate the risk and mitigate the risk. Means what is the risk which is associated with the different disasters across different cities, and what is the mitigation plan for that particular disaster in that particular city. So such type of plan is right now, it is not existing in our smart city plan, but we must have such type of plans. Some of the government initiative is also related with this. This is a study which is carried out by National Institute of Disaster Management, that is Climate Risk Management, CRM. But since this study has been carried out in some states, and carrying out such study at a state level is very difficult, because a state is a very big study area, so it is very difficult to collect the data very precisely and do the things in proper manner. So we need to conduct this study on a very finer resolution, like city level or like urban level, we can do that. So this is all about what is climate change, how it is happening across globally, how it is happening across India or smaller region, what the government is planning to tackle the climate change. But what is the problem, why we are not able to properly estimating the climate risk? What is the issue with this? Why we are not able to predict the climate change? Why we are not able to do the proper mitigation and adaptation to the climate change? What is the issue related to climate change at present time? So if we talk about this, right now we do not have do not have scientific information database. It is insufficient observation or scientific information database right now we have. Second, if we talk about this, we have inadequate knowledge on the disaster risk in different sectors of economy. We are just looking at some sectors of economy, because this climate change is affecting all the sectors. Either it is agriculture, natural ecosystem, health, biodiversity, coastal zones, etc. So we must have adequate knowledge regarding the effect of climate change on different sectors. And the very important thing is that, for example, I think you all are related to climate, you are working on climate change only. Some of them you are working on impact of climate change on crop or agriculture, or you are showing the drought conditions. How many of you have visited any agriculture or farmland during your study? means you have visited your study area. For example, if you are working on Bhopal, so have you visited any agricultural land during that? If you are working, if you are finding out the impact of climate change on the crop production like wheat or any area like Madhya Pradesh or Bhopal or any district, have you visited? Have you visited? Any other? Who is working on drought? Anyone who is working on drought? Have you visited anywhere? I think you are working on flash drought. So have you visited Rajasthan? I think you visited city. So if you are visiting Bhopal to DB City Mall or any other, then it is not related to your agricultural drought. You have to visit the agricultural land. Have you ever talked with farmers? For example, you have found out the drought conditions. Okay, this is the agricultural drought. So that is anyhow it is related to the farmer. End user is the farmer. Have you talked about him ki I am trying to find out the agricultural drought across your area. So this is the condition, and I am predicting the future drought condition, and this will be the condition. So have you asked anything or have you suggested them? So this is a problem across everyone, even with me and you, that we are doing the research for the end user, that is farmer, but we are not okay that we are going to him, we are talking to him, and we are giving some inputs that this is the issue. For example, if I have worked on the impact of climate change on some crop like maize across Bhopal, that paper will get published, I will get something from that, maybe I get promoted due to that paper, but the main purpose of that paper is not served, because a farmer will not ask the Google Scholar link or the paper or a DOI of that paper or a PDF of that copy that okay, send me this paper, I'll read and let me know what is the impact of climate change on the wheat. So this is the problem, that's why we are not able to tackle the climate change, because there is a poor connectivity between researcher and the end users, and this is causing the problem to tackle the climate change. Right now we don't have any framework that can incorporate the time evolving climatic parameters. So right now if we talk about this, we need a risk information conveying platform. What is risk information conveying platform? For example, if a district collector or collector is there, so he will able to understand what is drought, what is flood, how it can be determined, like what is SPI, what is SPEI, what is POT. He will not understand each and every single thing until unless he is a climate researcher. So if you are finding out the drought conditions or heat waves, so you should make some platform which is very user friendly, so that any collector or any administration person have that platform or that app in his mobile, and he can see the situation what will be going to happen in next coming 2-3 days regarding any climatic extreme events. So that type of risk information conveying platform is still missing across different parts. So it is very important that we can develop a E2 that can provide the risk across different particular area, so that any administration or policy maker can just see the things that what is going to be happen in next coming months or next coming days, so they can plan accordingly. But since as a researchers we know, but we are not conveying the information to them, so as a researcher we can't do anything on a policy making system. So we need a tool which should be related to this. So what type of tool we can develop? A tool which discuss about the climate risk estimation and assessment tool. Means a tool which can find what is the extreme climatic risk estimation and assessment tool. Why it is required? Because it can fulfill the requirement of climate extreme risk assessment platform. And for whom it will be useful? It will be useful for institutions, government bodies, researchers, students like us, and the private firms which are dealing with the climate change. So such type of tool we can develop, in which we can discuss or we can show the integrated online risk visualization platform. It means, what is visualization platform? It means in online way, in the real time, we can see what is the risk of any particular climatic risk or any particular hazard or the combination of hazards. The second thing is single and multi-hazard risk assessment. The problem is right now we are dealing with the individual hazard, but it is not possible that always a single individual hazard will come. It may come individually, it may come with other hazards also. So we must have single risk assessment or multi-hazard risk assessment. The third thing is identification of drivers for the extreme events. Means we must know what are the major drivers which are causing these disasters or hazards. And finally, we must show what is the vulnerability and what is the exposure to estimate the risk. Because if we are calculating the risk, we must know who are the most vulnerable community for that particular type of hazard. Because for every single hazard, there are different vulnerable population or vulnerable things related to that particular hazard. And what is the exposure? Because why we need these two parameters to calculate the risk? Because risk is calculated as hazard into vulnerability into exposure. So for calculating any risk, we have to we must have the data set related to hazard, then vulnerability, and then exposure. Okay, so we must develop a e-tool for a common people or for the researchers, for like you. For example, if a first year MTech student is trying to delve into the research team or research areas, he must have these data sets very easily. Means he should once he use this e-tool, he can able to look various risk estimate data sets. He will not able right now what we are facing, that initially for the very first year of MTech or PhD, students are looking for the data set. If they have a data set, they are not able to convert it. For example, if they are going for the IMD data set, they will see, okay, this is .NetCDF, what is it? How we will convert NetCDF into Excel file. If they are going for the temperature data set at IMD, it is .grd format, that how to convert .grd to the Excel file. So we need to develop a e-tool that should work like this. For example, there should be a tab that is named as risk estimation, in which there is another sub tab that is high rainfall risk. If student click on that, a map should be visible to him, and that should be real time map which is showing the high rainfall risk or extreme precipitation risk. Second sub tab should be drought risk, and if he will click or she will click on it, drought risk maps are available to him. Then risk to ecosystem productivity maps will be there, then resilience to drought and map will be there for that. So these are the visualization, but this is, I think, less useful to a researcher rather than the second thing, because you need directly the data set. So there should be a toolbox or download also in that particular website, and if we click on that toolbox, the sub tab will be open, that is data download, and in data download, or the second should be risk and resilience map. So once you click on the data download or risk and resilience map, you will able to get the data download, or you will able to download the risk and resilience maps across different study area, whatever the study area you have selected. So this type of e-tool is very useful or very required thing at right now, because we as a researchers are dealing with the data set and we are facing a lot of problems related to data sets. As a researcher, if we are feeling this issue, then think about the common person, farmer or district collector who is making the policy for the state or for the particular district. They are not able to get the data set. So such type of e-tool will show the data set on a real time. Then these are some adaptation and mitigation strategies. I think you know about the adaptation and mitigation strategies. No need to discuss this. Then simply I will discuss a very important thing. I think next lecture itself, Dr. Lixin Wang will discuss the IPCC. So I will not discuss much more about this. You know that this is the Intergovernmental Panel on Climate Change, which is an international body which is established in 1988, which is developed by the UNEP and the WMO. and there are some roles. So we know that IPCC do not conduct the research. It includes the research of different organizations of different researchers. So the role is, they will initially they will understand the thing what is climate change. So I will discuss what is the main composition or structure of IPCC. So there are 3 or 4 working groups of climate change, working group 1, 2, 3 and 4. So they have different works. Accordingly, initially they will think what is the climate change, what is the issue with this. Second one will work on the impacts, what is the impact of climate change. Third will suggest what is the mitigation part, and fourth one is check whatever the mitigation we are suggesting, what is the issue with it and how we can rectify in the better way. So these are some of the IPCC scenarios. I think you know that IPCC published the assessment report. So first assessment report is in 2001 and 2007 we have assessment report which have different climatic scenarios like A1, A2, B1 and B2, but since these are very old I will not discuss them. The second one is in 2014, that is known as assessment report 5, that is AR5, and in this they have discussed 4 climatic scenarios for the future, that is RCP, I think representative concentration pathways, and you have an idea about this. So as per this representative concentration pathways, they have discussed 4 important scenarios. The first one is 2.6 and last one is 8.5. So means they think like that if we are able to tackle the climate change in the near coming future itself, then the temperature will not rise very much, it will go up to 1 degree. And if we will not do anything mitigation, or if we will not able to tackle the climate change in the better way, and we are doing the emission in the same rate or we will increase the emission, then the temperature will increase up to 3.7 degree after the end of the century, that is 2100. In between they have also classified the intermediate scenarios, that is 4.5, and in that they have shown that this temperature increase will rise up to 1.8 degree to 2.2 degree. Then in 2021 they have published another assessment report, that is assessment report 6, and in this they have shared socio-economic pathways. Means instead of RCP they have developed the SSP. They have included different things according to economy also. So that is shared socio-economic pathways. So these scenarios will be discussed in deep by the Dr. Lixin Wang. So I will not take time in these IPCC scenarios. So next thing is that whenever we think about the climate or future prediction of climate, we must have a knowledge regarding the climate models also. What is climate models? So why you think that there is a need to model the climate? What is the use of climate models? Why we need the climate models? What is the use of climate model? Right, means right now we are in 2025. So we can expect that what will be going to be happen in 2050 or 2075, so that based on that we can make the policies so that it will not affect much to us. So a model is nothing but it is a simplified version of anything. For example, if you have to think about design a car, you have to make the model of that. You will not make the prototype. Initially you will go with the model and you will check what will be going to be happen in the next coming years. So there are 2 ways to model the situation, that is physical model and numerical model. What is the basic difference between the physical and numerical model? Which one is better, physical or numerical? Physical. Okay, means everything is available then physical or numerical? Right. So numerical model is better as far as if you want to do the research work within a very short period of time. If you want to work within a month itself, then numerical model is good. But if you want to do better study, then physical model is good, because numerical model have lot of disadvantages, because it is depending upon some of the input parameters, and based on that input parameter it is creating some relationship between that. Means whatever the input you have and whatever the output you want, you will make the relationship between that two parameters or three parameters, and based on that you are predicting the future things. So for example, if you are predicting the runoff based on the rainfall, so it will give a relationship between the rainfall and runoff, and based on that you can predict the runoff for the future. But there is a disadvantage associated with this, because you are giving the rainfall and you are predicting the runoff. What about the climate, what about the different other conditions of ecosystem? For example, you have rainfall of Bhopal and you have a data of runoff also. Based on that you have established a relationship between rainfall and runoff, and based on that you are giving the rainfall and you are predicting the runoff for the Bhopal. The same thing if I give the data set for the US also, the same, if the rainfall data is same, it will predict the same runoff for the US, same runoff for the Bhopal, and same runoff for the Delhi itself. So what is the use of LULC? What is the use of geographical condition of that particular place? Means if you have a rainfall data, you will have a runoff data accordingly, but there is no impact of geographical condition in that part, and we know that this is completely inappropriate information for the runoff, because maybe for example if you talk about the hilly areas, rainfall will be there but runoff will be different as compared to the runoff occur in the Bhopal district. So in that you have to include the geographical conditions of that particular area. So that is the advantage of physical models. So physical models are nothing but they are the replica of the same thing but in the smaller form. And numerical I have already told. For example, if you do the rainfall runoff modeling, you can do the rainfall runoff modeling. For example, you have data set from 1980 to 2020. So initially what you do, you will take the rainfall data and you have the runoff data for initial 10 years or 20 years. So based on rainfall and runoff data, there will be equation we can form. For example, you have a rainfall like from 1981 to 2021, out of which you have up to 2010. So this is rainfall, this is rainfall precipitation, and this is runoff. So based on these two data set, there will be a relationship created between these two data set in any equation like y equal to mx plus c. Once this equation is formed, in from 2010 to 2025 itself, you will give the rainfall data set and you will predict the runoff. So this is rainfall, this is runoff. If you will give rainfall as an input with some constant m and c, it will predict the runoff. So this is simulated runoff and this is observed runoff. So since you have observed as well as simulated for 2010 to 2015 25, what you do, you will find out the r square value, means how much how better we are predicting, because for this period you have simulated using this relation, and for the same period you have the observed data also. So based on that you will find out how better we are predicting the values. And if r square value is good, means for example r square is 0.8 or above than that, that means we are creating the relationship in the better way. So what we do, for 2026 to 2100 we will give the rainfall data set from GCMs, and based on that we will predict the runoff value. But the problem in this numerical model is that we are not considering the another important factors which are causing the runoff. The rainfall is not only the parameter which is deciding the runoff. There are other parameters like what is the LULC, what is the slope of that particular area, other geographical conditions. So in to show the better understanding of the runoff for the particular area, we must consider the geographical condition of that particular area, and for that we will take the physical model into the consideration itself. Okay, so these are some of the most widely used GCMs. I think you know about the CMIP 6. So initially we are using CMIP 5, but right now we are using the CMIP 6. These are some of the latest generation of GCMs. So these are developed by different institutions of different countries, and they are different features. But whenever you are going to use the GCM dataset, I suggest never use the GCM dataset directly, because there are some biasness or uncertainties associated with the GCM dataset. So there are different bias correction techniques through which we can bias correct the means we can do the correction in the biasness available in the GCM dataset. So bias correction is a mandatory part. So what are the different techniques to correct the bias data? There are different ways to correct the biasness in the GCM. The very simple way to correct the biasness is, for example, if you have 10 or 11 GCM dataset, the simplest way is to make the ensembles of the datasets. So that is known as multimodal ensembles. Means you are taking 11 models and you are making the ensemble of that. For example, 2 more GCMs are over predicting the data, 2 are underestimating the data, 2 are over predicting the data. So what you will do, you will take the average of that. So that will somehow give the correct value, but not the exact value. The second important bias correction technique is very simple. I think you can do. There are various techniques for bias correction, but the simplest technique for bias correction is एक बार ये देख लो कि लिक्सिन महंगा आ गए गेस्ट हाउस में. So the simplest way to do the bias correction is, for example, you have some GCM and you have data set of GCM, for example, precipitation. So in precipitation, if we talk about RCP or SSP, for example, we are opening RCP 2.5 folder. In this we have precipitation, we have temperature and other data set. In the precipitation, this precipitation is divided into 2 temporal way, 1970 to 2025, and since it is older one, so maybe it is around 2021, and 2021 or 2022 to 2100. So you will get the precipitation, that is raw precipitation data set, or before bias correction precipitation. So since you know that for this period from 1970 to 2025 we have observed data set also, which is given by the India Meteorological Department. So we have IMD data from 1970 to 2020, and we have raw PCP raw data from GCM. So we are not confirmed that whether this data set provided by GCM is correct or not, but we are very confirm about this data set which is given by the India Meteorological bias corrected after using IMD data set, and this is the bias corrected precipitation data set. Or similarly we can use this approach for the temperature or other parameters also. So this is the simplest way to do the bias correction using this. So this way is known as which method of bias correction? It is quantile QQ mapping. So if you want to see the result of QQ mapping for bias correction, this is one of my paper. So you can see that before bias correction this is the data set, and after the bias correction it is looking like this one. So bias correction can be done like this. These are some of the GCMs, how to download the GCM. These are the links provided for that, and the data format is .nc file, that is .netcdf file. Then I think yesterday itself we are discussing about the downscaling. So we need to show that what is downscaling. So what is downscaling? Means whatever the data set we have at bigger resolution, for example, whatever the data we have available for the Bhopal, and if we want to make that data set available for the Manate, that is downscaling. Means the data set is available at Bhopal, but we need to take the or download the data for the minute itself. So that process is known as downscaling. Means the spatial resolution which is available at course, we need to produce it at a final resolution from the GCM to RCM. That is downscaling. So there are two types of downscaling. One is dynamic and second is statistical. What is the basic difference between them? In statistical downscaling, what is the important thing to include? What is the input required for the statistical downscaling? Historical data, right. Same like this. This is the requirement of statistical downscaling. If we want to downscale the data set, we must have historical data set. This is the advantage and this is the disadvantage also. Disadvantage is like, because for the statistical downscaling we need historical data, but for a longer period, minimum for 20 years minimum, but desirable is 50 years. If we have 50 years data set, then only we can perform better downscaling itself. Okay, it's already 10. Give me a minute. Yeah, I'll ask the
Yes.
Yes. Is on?
Start.
Just like that. Hi, good morning, everyone. Yeah, since I'll be going to talk with you guys for a couple of days, I thought it's good I start to introduce myself a little bit and also talk about my institution, and then we start talking about the lecture material. So first, I will talk about the IPCC report. So essentially, we'll focus on some fundamental concepts about the IPCC report. We only have time for a very small proportion from the report. And then I will use some case studies in the next couple of days to talk about drought, talk about flooding, and different things. So yeah, I guess maybe first just introduce myself a little bit. Yeah, again, first I want to apologize for being late. Yeah, somehow the driver forgot to pick me up this morning. Currently, I'm a professor at Indiana University, Indianapolis, which is located in the center of the U.S., very close to Great Lakes, very close to Chicago. If you know the city, is about 3 hours. So that's what it looks like in my city center. So I came from China originally. I got my bachelor degree from Hebei University a long time ago now. And after I got my degree, I got a bachelor degree. I got a fellowship. I came to the US for master degree at the University of North Carolina at Greensboro. I spent 2 years there and finished my master degree, and then I went to University of Virginia for PhD, majoring in environmental science. And then after that, I spent about 3 years as a postdoc researcher at Princeton University in C1 Environmental Engineering Department. I think similar to many of you guys here. And then after that, I got a fellowship from Australia, University of New South Wales, it's called Vice Chancellor Fellowship for 3 years. So I moved to Australia there, but only like a half year. But when I was there, I got a job offer from my current university. So this is permanent position. So this is just like a 3-year position. So I just gave up the fellowship and moved back to US, and I was here since then, for about 11 years now. So that's kind of my trajectory. And so, over the years I've been doing, I think, a good research that recognized at different level, like from my university. I got the President Bicentennial Medal. It's only a few from the university guideline. And the national level, I got called National Science Foundation Career Grant. So that's also a big honor too. And internationally, I have been writing many papers, and they got used quite often. So I got recognition as a highly cited researcher from 2013 and last year as well. So yeah, I guess the point here is not bragging myself. It's really just to give you the idea. If I can do it, everybody here, you can do it as well. Right? I start from a kind of academically like a modest status. Like my university is good university, it's a good state university, but not the very top ones in China. So, but I can still, work hard, dream big, and keep working hard until you can, achieve the dream you want. I guess the idea is, if you have a good dream in your academic world, keep doing on that regardless where you start. So the field of my research is called eco-hydrology. Simply speaking, is basically I'm looking at the interaction between vegetation dynamic and the water cycle. So there is a two-way interaction here, and the interaction is controlled or influenced by the soil condition, but also by the atmosphere condition. So that's make the interaction more complex. So I'm looking at this interaction from different scales. From individual plant scale all the way ranging to global scale. So in next couple of days, most of example will talk about as a larger scale ecosystem to global scale, but we do look at things at a different level. And the key question in my group is really we try to look at the impact of climate change on the interaction between vegetation and the water across different scales. Over the years, my group has been publishing widely, like in different journals. A lot of them are in the top journals, nature groups. So again, that's the same idea, right? So I guess keep working hard, dream big, and you should be able to achieve a lot of success along your career. So enough about me. And this is a university I work now. Right? So that's it's called Indiana University Indianapolis. So it's one of the several campuses belong to Indiana University. So there are several like UC system, UC Berkeley, UC LA. Right? So there are different campuses. We are one of them, and we have about close to 30,000, 25 plus thousand students on our campus, and it's quite diverse. You can see there are students from 100 plus countries, right? So it's actually quite a diverse body. In fact, even our chancellor is actually from the Indian region, Dr. Rasa Ramahan. So I think she graduated from one of the IIT schools. So we have a lot of degrees, right? Close to 400 degree certificate program, and we have in total like 17 schools. And in terms of research funding, there every year a lot of research money coming to the campus. So we have a school of medicine of Indiana University located in our campus, but when we count for the research funding, typically they are separated because they get just so much money. So it's they kind of independent in many ways. And we have a lot of research centers and research institute. So I'm within. So the university is an urban campus, right? So it's in the capital. So it's we consider it's a premier urban campus in the U.S. So because Indianapolis is the capital of the state, is quite culturally diverse and has a lot to offer. There are different rankings. Again, the university is not the one you hear every day, but it's a decent, it's a research intensive university. So I'm out of the 17 schools, I'm within School of Science. That's one of the 17 schools within our university, and we have 6 departments. So biology, chemistry, math, physics, psychology. So I'm in the department of Earth and environmental sciences. So just a couple of slides about this particular program. Right? So we have a kind of a different bachelor, master, and PhD degrees. We have a bachelor degree in geology, and also we have a bachelor degree in environmental science. We have a master degree in geology, and then PhD in applied earth science. So that is a interdisciplinary PhD program. That in the past, I have a student that has an engineering background. I have a student with a biology background. I have a student with a physics background. Right? So it's actually quite diverse PhD program. You can have a student from very diverse background. So I guess the idea talk about this is, I know you guys, some of you guys are master students, some are PhD. Right? So if you are interest in pursuing your degree for a master's student, for example, you can talk with me about the planning program here. Right? So in US, in general, if you are working on a master or PhD program, you always get fully funded. Right? So if they don't have money, we typically don't take you. Right? So that's typically the program, how a program runs. You don't have to pay yourself. Like myself, right? I got fully support doing my master and PhD degrees. And for this department, we have it's relatively small department. We have 13 faculty members as a specialty in different areas, some in hydrology, some in geochemistry. We have a lot of very advanced instruments and techniques like people use in different fields of geoscience. Personally, I have two isotope instruments using for hydrological investigation. So our program has about 100 undergraduate students and about 30 graduate students in our program. And all the faculty has research fundings come from the National Science Foundation, NASA, USDA, USGS. So there are pretty diverse research within the department. So yeah, I mean, just very brief to talk about my journey and also the university I work with. So if you want to pursue an advanced degree, or if you're a faculty member here, you want to do Fulbright, we do have every year there are several Fulbright scholars from different schools in my university. So yeah, that's just a very brief background. And then my plan is we'll go to the IPCC report. We'll just touch on some of the important concepts today. And then later we'll talk about some case studies. So how many of you guys heard of IPCC reports? You raise your hand. Good. Good. Yeah. So how many actually read IPCC report? Have you read any of IPCC report? Not really, right? So that is interesting thing. Yeah, when I teach my own class in my university, right? So actually, there are even less percentage of the students actually know IPCC report. They never heard of IPCC, right? So I mean, for you guys, majority actually heard of IPCC report. Right? That's good, but very few actually have the chance to read the report itself. Right? So IPCC stands for Intergovernmental Panel on Climate Change. That's IPCC. Right? So it's basically a United Nations body. Right? So that's their function is to try to. We'll talk about their function in the next slide in more detail. But really, this United Nations body try to assess the science related to climate change. That is the IPCC stand for. Right? So, and they're in their own word, that's IPCC talk about their own role. Right? So basically, they will take a very comprehensive approach, take a very objective approach, and a transparent approach, try to assess all the available information in the literature related to climate change. So that's the kind of aim of this body. And they try to stay neutral in terms of government policy, right? So, but they do keep policy implication in their mind, right? So that's the idea. They try to. So that is the role of IPCC. This is kind of a brief history of IPCC. So IPCC was established in 1988. Right? So that's a joint establishment by WMO, World Meteorology Organization, and the UNEP, United Nations Environmental Program. So these two agencies from the United Nations established the IPCC. And then, as time goes by, the milestone of IPCC are these ones. FAR refer to the first annual assessment, first assessment report, second assessment report, and then third assessment report. So from the fourth one, they changed to assessment report 4, 5, right? So things like this. Right? So that's a kind of timeline of different report, which year they were reported. And then they have some kind of a special report. So special report 15 basically talk about, if we have a 1.5 degree Celsius temperature increase, what the world look like. Right? So that's kind of a special report. And the most current, the most updated report is AR6. So that's was produced in 2022. So that is kind of a timeline of IPCC report. You can see as time goes by, the scientific literature related to climate change has been expanding dramatically, and so that's why people need to assess more and more information. That's why IPCC report, every report take about 5 years, 5-6 years. So because there's a lot of information people has to put it together, so it's take time. So this one is from IPCC report. So in my class in the university, I use IPCC report because it's public available, and so it's you can freely download from their website, right? So it's actually you can download individual chapter of the whole report. So it's actually very handy to have that. And all the figures I show you here is actually from the report. It's all public available. You can access that. And this is kind of the procedure IPCC produce their report. They do scoping, they prove the timeline, and then each university, each countries will recommend authors for IPCC report, and then they meeting together. So it's a long process. There's a lot of meetings involved, planning, review the report, and the final proof. So for final proof, they actually prove line by line. Everybody has to agree. It's actually a very tedious process. So this is the kind of structure of IPCC report. They have really like 3 working groups. The working group 1 is mostly focused on the physical science, and then the working group 2 is focused on the impact of climate change, and then working group 3 is talk about what the mitigation strategies you can use to mitigate the climate change impact. And then there is a task force specifically for like doing the inventory for greenhouse gas emission. So they are the kind of 4 major groups within IPCC doing things, and each group will produce their own report. So the report I'm using mostly the first group is the physical science one. Right? So talk about what's the most updated understanding of the climate change information. So they try to have a kind of intervene between the plenary session is that everybody meet together to discuss the final report, and the bureau is basically the different groups. So there is an interview between the kind of the policy side and the science side. Try to they try to stay neutral, but they try to make human influence on climate system is clear. So in the AR6, the language is even more stronger. And then we talk about the more we describe the climate system, the more risks we are facing essentially. And then the third one is a kind of a positive uplifting note to talk about. We do have means actually to mitigate the impact if we do things. Right? So that's kind of the 3 key messages from IPCC report. And their biggest achievement, we probably know, is the group as a whole. They were awarded the Nobel Prize in 2007 as a recognition of their role for informing people about the impact of climate change. So this is what AR6 look like. Right? So that is AR6, the physical science report. So you can see, I give you an example of the chapters. There are 12 chapters. You can see there are more than 2,000 pages. It's a very large report, right? So that's why nobody read it, right? So it's just very dense report. But to me, it's actually the best scientific literature regarding climate change, right? So even they are really trying to put in a way can be digested by anybody, but of course it's written by scientists. It's still dense sometimes. It's not very easy to read, but it's not like terribly hard to read. So I would suggest all of you guys, like if you're doing climate-related research, that should be our starting point. Actually, they are written by leading scientists in the field. They actually doing the literature review already for you, right? So they already tell you what the most updated status of a certain area, right? If you're doing research in any area, you should check what's the current status. Then we can just talk about some of the major concepts concept, the key concept in terms of climate system, right? So the first one is basically the difference between weather and climate, right? So in climate deniers, right? So they always talk about sometimes, today is so cold, why we talk about climate change, or this winter is so cold, why we talk about climate change. So because they try to, in a way, or they just get confused about the weather events and the climate events, right? So when we talk about weather, we talk about the atmosphere conditions, like a very short time scale, right? Days, weeks, right? So, but when we talk about climate, we really talk about average weather condition over a very long time. And for the WMO, they define climate, you actually have to talk about average over 30 years period, right? So we are actually talking about the moving average of the weather condition, using long-term average, like 30-year moving average, right? That is a big difference between weather and climate, right? So, but even weather, right? So, some people talk about, today is super cold, why we talk about global warming. So actually, climate change is not only introduced just warming itself, right? It's really the big variability of the climate, right? So in Indiana, for example, we are in Midwest in the US, right? So in winter it's mild, it could be cold, but there are some days could be super cold, right? So part of the reason for that is because of the changing climate, they make the polar vortex very strong, right? So the cold air sometimes can escape the polar vortex and get into the Midwest region, right? So climate warming actually sometimes could bring cold weather. So that's sometimes it's counterintuitive, but that's true. So the second important concept is radiative forcing, right? So really when we talk about how things affect warming the climate or how things cooling the climate, we really talk about their radiative force, right? So radiative forcing in definition is basically a measure of the energy balance change in responding to whatever the disturbance you're talking about, either more CO2 you put in the atmosphere or more aerosol you inject into the atmosphere. Right? So that's, we are talking about the net change in energy balance. So, when we talk about positive radiative forcing, essentially we are talking about this is the warming of the climate. Right? If we talk about negative radiative forcing, we are talking about this is the cooling the climate. Right? So in our climate systems, most of all the greenhouse gases, right? So they are very strong. They have a very positive, very strong warming potential because they have a positive radiative force. And for the occupied almost, the ones, non-use is also negative radiative forcing overall, but the aerosol is kind of the factors, the most powerful cooling radiative forcing. So they can cool the climate. Right? So that's why a lot of people talk about the geoengineering. Right? So if we get to the point, the warming is out of control, you have to do something. Right? So one thing people talk about is really the kind of injection of the aerosols into the Earth's atmosphere. So that will have immediate cooling. Right? So of course that has unknown consequences. Right? We don't know how much the impact on human health, for example. Right? So people, that's our kind of last resort. Right? You don't want to do that. The most effective is still we're cutting down the emission. Right? We're cutting down all the greenhouse gases. Right? We try to not go to the resort. So that's but that is basically when we talk about the climate forcing, you need to know what is radiative forcing, what that's referred to. So feel free to stop me anytime if you have questions. Right? So I need to be interactive lectures. So another important concept basically is positive and negative feedbacks is in the climate system. Right? So this one is different from radiative forcing. Right? So when we talk about positive and negative feedback, we are really talking about the kind of the process. If we talk about the positive feedback, we are really talking about a process accelerating whatever the process already going on. And the negative feedback talking about the process will slow down or put a brake on the process, on the warming, right, in this case. So this is also a figure from IPCC report to talk about the different positive and negative feedbacks in our climate systems. Right? So positive ones are typically easier to understand. For example, when we talk about water vapor, as why we call water vapor is a positive feedback, because if you have a warming happens, right, so then you will have more evaporation. More evaporation will basically produce more water vapor in the air, right? Because water vapor is a very strong greenhouse gas, right? More water vapor in the air will make the warming even more quicker, right? So that's why we call positive feedback. Is actually accelerate the whole process, right? So but if we think about the negative feedback, basically we have to think about that is the process actually slow down the warming, right? So for example, for long wave radiation, right? So that's essentially is because Earth is a black body, right? It's always emit energy, right? But if you're warming the Earth's body, so there will be more emission, the energy emission. But more energy emission means less heat or less energy in Earth. So that means the warming will be slowed down, will be less further warming. Right? So that's why it's called negative feedback. It's really the process actually break down or slow down the warming. Right? So that's a big difference between positive and negative feedbacks. Any questions about the positive and the negative feedbacks? So anybody can describe, for example, for snow, ice, albedo, right? So that is actually positive feedback. Can you try to describe why that is a positive feedback? So you can start. So typically we will start from warming, right? So warming will make certain changes in snow and ice albedo, and that changes essentially should accelerate further warming. That's why we call it positive feedback. So, but somebody can describe in detail what the process look like. You don't be afraid to, don't say that. Yeah, just have a try. Or we can do together, right? So if we have a warming condition, right? So how that will impact the snow and ice albedo, increase or decrease? Yeah, this one I can't hear you. Yeah. Yes. So if you have a warming condition, what's the impact for albedo? Is it increase or decrease? If you have a warming condition, that will melt the snow and ice, right? So when you have a melting of snow and ice, do you increase or decrease albedo? What is albedo, I guess? It's a reflection, right? So if the ice is gone, whether that's increase or decrease albedo? Increase. Right, it's increasing, right? So, if you have a warming condition, the snow and ice cover will be lower, right? So that means you increase the. Oh no, sorry. So if you have a less ice, whether that increase or decrease albedo. Albedo is a reflection, right? So if you have ice, actually it's very good at reflecting the energy back, right? If you have less ice, that's a higher and lower albedo. So less will be reflected, right? More will absorb, right? So that will be less, the albedo will be less, right? So it's actually lower albedo. But lower albedo means less will reflected, more will be absorbed. So that will be make the melting even more and the albedo even lower, right? So that's why it's a positive. It's actually make the albedo like less and less, but also the warming higher and higher, right? So that's why we call it is a positive feedback. Yeah. Yeah. Thanks for trying. Yeah, that's good. That's good. So I guess when we talk about the future climate predictions, right? So sometimes it's very hard to do just because a lot of the complex feedback within the Earth system, like clouds, you can see, there are both positive and a negative component, right? So it depends on the location of the clouds, depends on the type of the clouds, right? So some clouds has a positive feedback, some clouds has a negative feedback, right? So that's why climate itself is quite complex when you predict the future climate response. So later we will talk about the complex response. We will touch that again. But the point here is really try to understand, what is positive feedback, what is negative feedback, and you can try to use your word to describe what look like, right? So maybe, for example, for air CO2 exchange, right? So this one, for example, if we have a more CO2 like in the atmosphere, right? So that means the exchange will be more, right? So there will be more CO2 basically stored in the ocean, right? So there will be less in the air, right? So that's why is a negative feedback, right? So that's is actually kind of reduce slow down the process, and the positive is accelerating the process, right? Just make sure the major difference between these two. So for different IPCC report, there are different policy contact. So the first IPCC report, FAR, so that's why it's actually is a foundation for the UN Framework Convention on Climate Change, UN by FCCC. So that's why it's actually is a very large framework people use to fight climate change. So FAR, the first assessment report, is a foundation for this framework. And the second assessment report is actually the foundation for the Kyoto Protocol. So that is the first major international agreement fighting climate change. That is called the Kyoto Protocol. Right? So what's the second one? This is the first one. What's the second one? Or the most recent one? So the first one is Kyoto. What's the second one? What's the recent one? What's that called? So the second one is called Paris Agreement. That's 2015. That's the most recent one. Right? So that one is basically rely on the AR4 and AR5 report. So both these reports provide a foundation for the Paris Agreement. So the major difference is for the Kyoto Protocol is almost like a volunteer participation, right? So there's no very clear enforcement. But for Paris Agreement is more structured, try to make people really doing the work, right? So it's a little bit much more rigorous in a way, try to get the results. So the really the goal of Paris Agreement try to let the whole human society as a whole try to fight climate change, let the temperature below 2 degrees C, and hopefully below 1.5 degrees C compared to the pre-industrial period. So that's the goal for Paris Agreement. Of course, some scientists already worry, even right now, we may already pass the 1.5 degree mark for the end of the century. So that's definitely discouraging, but many think we still possible for the 1.5. But I mean, the point is there's no magic number like 1.5, 1.6, 1.7, or 2, right? So really, the more we do now, the quicker we do now in terms of the reduction in emission, the less variabilities, the less harm we make for our future generations. Right? So science is very clear on that. So it's really how do we actually react to this. So in ER6 there are some kind of a newer concept, new foundations people talk about. Some talk about earlier, people emphasize again. Right? For example, people talk about the baseline, people talk about reference period, people talk about anomaly. Right? So here I just give you a definition for this. So baseline basically we refer to kind of the average from the reference period. That's our baseline. Right? By name you can see that that's the ones we compare to. Right? That's our baseline. And the reference period basically you talk about a period you compare other period with. So that's the reference period. And anomaly is really talk about, remember anomaly is not like English meaning in terms of, is very different from others. But anomaly in climate scenario here is has a specific meaning. Right? So really, when we talk about anomaly, we talk about the difference between the current observation from your baseline. So the difference is anomaly. Right? In climate reporting, a lot of time we always use anomaly to do the trend. Right? So here I'll give you an example. So you can think about why we don't use raw value, why we use anomaly. Right? So here is a different climate model predictions about the temperature trend from 1850 until the end of the century. So each line refer to each individual model, and then you have observations here. Right? So and then there are different ways to present that. But I guess based on this, based on your understanding of what is a baseline, what is reference period, what is anomaly, why people tend to prefer using anomaly rather than this is absolute value, so the kind of raw data, and this is anomaly. Why people use this, not this? So what's the advantage of using anomaly in presenting the climate data? So basically, I talk about minimize the variability, right? Highlight the trend, right? So yeah, that's exactly one of the major reasons people use that, right? So you can say for individual model output, right? So they don't necessarily agree with each other exactly, right? So every model has their own bias. Some maybe perform better in certain region or certain time period, and the others may perform better in other scenarios, right? So they all have their certain bias, right? So, but you can say, if you use anomaly, essentially are talking about you use, even they have their own bias, right? So because you use the observation minus the reference period, you actually get rid of that own bias in doing that, right? So, but by doing that, you can actually highlight how things are changing more clearly, right? Rather than look at the variability here, right? So that is a key reason people using anomaly rather than the like absolute value, right? So because all the observations, all the models may have their own bias, right? So the same for observation, right? So many people are measuring temperature, right? So across the global scale, but you may use a different thermometer, and they may not calibrate exactly correctly, right? So they may not really exactly the same. When you're using different data set to do the global average, there may be a bias in each different data set, right? But if you just keep using the same thermometer over a long time, even it's not reading correctly, but there's some systematic error. But if you're using the trend, using the difference, and you get rid of that small error, you can then compare from this location to this location in terms of the trend. You don't need to worry about the individual thermometer or how accurate they are. Right? You're talking about the trend. Right? So that's also part of the reason people prefer using anomaly, because you highlight the trend, you can then use a different data set to compare different regions, see their trend is faster or slower compared to different regions. Right? So yeah, just make sure you understand the power, the advantage of using anomaly rather than using the raw value. And also I want to introduce a concept. You need to know what is the CMIP6. Right? So CMIP6 stands for Coupled Model Intercomparison Project. Right? So that's basically by far the largest group effort. People try to compare different models and try to see how well they agree with each other, right? How well they agree with each other in terms of which region, where they are. Right? So it's basically a comparison of a comparison. It's a very large comparison. You can see there are already different modeling groups. They actually making the comparison. For example, some group maybe focus on ocean, some focus on land surface, and some maybe focus on paleoclimate. Within each group, they already have many models they compare with each other. And then the CMIP is basically you compare all of them all together. So that's why it's very large group effort doing the model comparison, make sure we have the most updated understanding of our model predictions. So the most current version is 6, CMIP 6. So that's typically CMIP is the same status as the IPCC report. We have an IPCC report AR6. So that's why CMIP is also on their 6th version. Right now, CMIP scientists are doing on the CMIP 7 now, and people also try to work on AR7 as well. Right? So they always parallel to each other. So another important concept I want to highlight is climate variability. Right? So we need to know climate does has their own variability. Right? So yearly variability is always there. So regardless what parameter you are looking at, either temperature, global temperature, regional temperature, or you talk about like a CS volume or like a coverage, they all changing year by year. Right? So that's the inherent nature of a climate. Right? But we need to recognize that because for example, we know climate has a big variability, but if you use very small data set. For example, we know global temperature is increasing, but if you only use maybe 5-year data from here, you can actually have a conclusion global temperature is actually declining. Right? So the same here, for UK summer temperature overall we know it's increasing, but if you only pick these 10 years, if you run a time series analysis, you'll get a conclusion UK temperature is still declining. Right? So, I guess the point is when we think about the climate, you have to think about long term. Right? So, sometimes if you use like a short term data, you could have an opposite direction from the long term trend. Right? So for CS extent, we know it's declining at a global scale. But if you look like a small period, that's blue line like here. If you run the Mankanda like a time series using this data set, your conclusion is the CS is actually increasing. Right? So that's incorrect for like a long-term trend. So that's the point of climate variability. And also, even with climate variability happening, right now, based on the record we have from other continents, right, we know there are called emergence of a climate change signal. Even with the climate variability we have for other continents, we actually see the climate change signal is there. Right? You can see. Right? Sure, there are different continents, the climate variability is different, but in North America, in US, right, for example, the climate variability is actually much bigger compared to South America or Africa. Right? So their variability is actually smaller. Like Europe and America, actually, they have very large climate variability. But even with the variability, we actually saw the climate change signal. Right? So it's actually quite clear there. So that's these last two slides really just try to emphasize we know there is a variable climate, right? It's always changing. That's why we use a long-term data set. We don't use like a small section of the data to look at the change. But also, even with the variability we know as it is, we actually clearly see the signal, the climate change signal from all the continent, right? So that's a kind of a key message here. So, like when you read IPCC report on climate record in general, we know there are always uncertainties in our future predictions. So here IPCC summarize, kind of the major sources of uncertainty in terms of both observations and the model or projections. So for observations, like I mentioned, you could have the instrument wrong or systematic error, right? Could be random, inherent randomness in climate system, but also could be instrument problem. Right? So that is uncertainty. But for future projections, there are actually different group of uncertainties there. The biggest one, I would say, is the radiative forcing uncertainty. So that basically means we don't know how much more CO2 will emit in the future, in terms of human society. Right? So we may cut them very big, but we may do business as usual. Right? So, that is the largest uncertainty in climate projection. And another is the climate response uncertainty. We talk about, there are positive, negative feedback in climate system. So climate response always have some uncertainty. For example, the CIS, the degree of CIS accelerating their disappearance is actually faster than scientists predict, right? So that's actually a surprise. So that is a climate response uncertainty. So uncertainty doesn't have to be one way or another. It's not like it could be faster or could be slower. Right? So that's uncertainty. And also the natural variability, like climate has their own natural variability. Right? So for example, there could be a big volcano eruption somewhere. Right? So that one, we know the large volcano eruption has a very large impact on climate systems, right? So, like in Philippines, like the one erupted in 1997, right? So that actually has a global cooling effect for about a year. So it actually has a very large global consequence. We, as a human being, we never be able to predict, exactly where the large volcano eruption will be. We can predict maybe shorter time scale within weeks, months, from the seismic activity, but you can't do the long-term projection. Right? So that is uncertainty. And then the interaction between climate variability and the radiative forces, that's another uncertainty. Right? So the last one basically is the model itself. Right? So model is not perfect. Right? So it's always a simplification of the actual system. There are always uncertainty there. Right? So that's basically the kind of the sources of uncertainty in future climate projections, the major source. So here, just give you the kind of a model projection uncertainty example. That's a figure from IPCC report. So you have a global temperature projection, regional temperature, and that has rainfall projection. So really, the key message I want to show you here is, there are different scenarios. The lower emission scenario, the higher emission scenario. Each scenario, you can see there are very big spread from individual models. Right? So, you can say one message you can get is if you compare temperature, global temperature and regional temperature, the regional temperature tend to have a bigger spread, so the uncertainty is larger. And also, if you compare temperature and the precipitation, right, you can say the temperature, the uncertainty is much smaller, the precipitation is much bigger. Right? So, depends on the climate variable you are looking, the uncertainty is different. And also depends on the global temperature prediction or regional temperature prediction, they are different too. And also, it depends on how far you look into the future. Right? So, if you look at more like a near future or far future, you can say even further away you are predicting, the more uncertainty that will become. So that is another message. So that's why for IPCC report, we never just use a single model result. We say, okay, the future will look like this. that's not good, right? So we're actually using a term called sampling, right? So basically means you actually average all the available model predictions. You actually, make you can say you average all of them, you get, results. So that's tend to be reduced much significantly. So that's the concept in sample, right? So you don't take prediction from any single model. You're actually using the average. So that's in simple word about in sample. But in sample you can do many different ways. You can actually, in sample the most common one you can do the kind of just in sample the output, model output. But you can also in sample the initial conditions. For different models, you have a different initial condition. You ensemble you make average all of them first, and then you run the model. That's the initial condition example. So you can also ensemble the parameters of different models. There are different ways people do ensemble, but the idea is, you never report results from one single model, but you're actually always doing that in an average manner. So maybe let's finish this 2 slides, we'll finish. So because we know uncertainty is always here in IPCC or in climate system, so in IPCC report, people try to deal with uncertainty in a very active manner. Right? So there are 2 ways people do deal with uncertainty. One is a qualitative, right? So that's a qualitative way. So people use confidence level, right? So whether what level of confidence, you could have a very high confidence, you could have a very low confidence. So that's a qualitative way to deal with uncertainty. So how do you do that? So this basically just based on the number of evidence you have, and then how variable between all the evidence. If I have a lot of evidence, robust evidence, and all the evidence point to one direction, high gradient, so that means you have very high confidence. But if you have a very limited evidence for certain things, and also even with this evidence, they, from a lower the place, low gradient, so that's, it will be very low confidence. And then there will be some in between, right? So you have a lot of evidence, they don't agree with each other very well, that's a kind of a medium kind of evidence, medium confidence, right? So there are a lot of in between. So, but this way is more qualitatively, right? So it's not based on numbers, really just based on how many evidence you have, how what level of agreement for this evidence. And then another better way for quantifying uncertainty is using the likelihood. Essentially, I'm using probability series, right? So that's if you have a probability of 99% above, we call virtually certain, right? If you have a 0.1% probability, we call exceptional unlikely, right? So and then they're based on the probability threshold, people will call virtually certain, very likely, right? So when you're reading IPCC report, when they use this word, they don't use randomly. It's actually based on the probability likelihood from the probability part. So it's a quantitative way to measure the uncertainty. So I guess the bottom line here is IPCC does recognize there are different uncertainties in our climate projection or just climate record in general. They try to have 2 ways to deal with uncertainty. Qualitative way using confidence level, and then quantitative way using likelihood, so using probability functions. Right? So when you're reading them, keep that in mind. I think let's stop here for the first part. Really just give you a sense, what IPCC report is, how do they work, and what are the kind of major concepts in climate system relevant to the changing climate. So I'll be here if you have questions, and you can come to me. We can talk related to this or any other questions. I'm happy to chat with you. All right, thank you, guys. Thanks. Any questions? Yeah, you can come to me if you have specific questions.
sir currently serves as the visiting professor cum outreach advisor at Indian Institute of Technology, Dharwad. In this role, he also coordinates the GYAN program, Global Initiative of Academic Networks program, fostering international collaboration and academic excellence. Professor Jayakumar sir illustrates career over 4 decades. He has held various esteemed positions, including Professor HAG and Dean at the National Institute of Technology, Warangal. His research interest includes hydrology, water resource management, climate change adaptation, and environmental management. Beyond academia, he contributes significantly to the environmental conservation as a member of the governing body of Wetland International South Asia. So please join me in welcoming Professor K.V. Jayakumar sir.
Thank
Over
you.
to you, sir.
Yeah, thank you. So I'm very happy to be part of this GYAN program, and let me share my presentation.
Sure, sir.
Is my screen visible?
Yes, sir. Yes, sir.
Yeah. Is it visible, right?
Yes, sir. Yes, sir.
Great, great. Yeah, welcome to this talk, the participants from various institutions. And next 1 hour, I'm going to talk on droughts, especially to climate change perspective, and giving a couple of case studies which I had carried out in the past 4 or 5 years on drought. Let's, start with working on water resource. I'm a 1978 graduate, and not too many people are interested to work in water resource. Civil engineering means structural engineering, geotech. So some of us decided to work in water, and that was the time a very beautiful quotation I read by John F. Kennedy in 1962, when at the time of Nobel Prize Award ceremony, he made his speech. One to solve the problem of water should be awarded 2 Nobel Prizes, one for science and other one for peace. Today, you find people fighting for water everywhere. Of late, we also know the Indus river being shared with Pakistan and India. We have a problem there. So solving water problem is a very important thing that has been attracting attention of the world. Now, as engineers, there is something which it's a Venn diagram which shows that you love what you love doing. You love civil engineering, you love water resources, and you're good in that, and you're getting a job in the same field, and the world also needs such people. So the intersection of what you love doing and what you're good at is called passion. Intersection of what you're good at and what you get paid for, that's profession. And intersection of what you can be paid for and what the world needs, a vocation. And what you love doing is the same as world needs, they're called mission. So today, we need whatever you do, you love whatever you're doing, you must be good in whatever you're doing, and you get a job in your area, your specialization. And world needs a lot of good people today. And there's a time when civil engineering is not having the importance that it really deserves, but you find 5 years from now, all of us will be in great demand. Now, you look at the amount of water that is available in the world. The total water available in the world is 96.5% is in ocean, and you find 2.5% is fresh water. The expand is fresh water. You find only 1.2% of the fresh water is the surface and other fresh water. The expand is you find in the fresh water, you find most of it is in ground ice and permanently frost. You got 20.9% lake, but just look at the rivers are 0.49%. The swamps and marshes are 2.6%, much higher. The amount of water in the soil is about 3.8%, atmosphere 3%. You find rivers have only 0.49% of the 1.2% of the fresh water, of the 2.5% of the total water available. So this shows that the amount of actual water available for us is very, very limited, but then that is enough to meet all our needs if we properly manage. So just look here, you find there's a total amount of water available, and that's the amount of liquid fresh water, and a small dot here is the fresh water of lake that's available to us. So this was a picture given in the year 1993, which is still valid. There's not much of changes taking place. Now look at our country. The area of our country is 329 million hectares. It has got 12 major and 14 medium river basins. 4% total average runoff of the world is in India. And per capita availability of natural runoff is just about 2,000 cubic meters per year. It's about 1/3 of the per capita availability in USA and Japan. And you find as the population increases, the per capita available water will keep decreasing. So this is something which all of us have to keep in mind, that we have less just equal to or less than 2,000 cubic meter per year per capita. Now, if you look at the rainfall that comes here, our annual precipitation is about 4,000 cubic kilometer. How did this come? This comes from the area of India and multiplied by about 1,100 millimeters of average rainfall, because annual precipitation is around 4,000 cubic kilometer. And the average annual runoff in various river countries around 2,030 cubic kilometer, which includes surface and groundwater. And 80 to 90% annual runoff occurs during monsoon months, which is June to September. Even this is now changing. That the total number of rainy days have drastically reduced now. The climate change impact, the rainfall the onset starts late, the withdrawal starts early. The total rainfall comes in less number of days, causing floods during the rainy season and drought for the long extended period. So you find the potential water available in India is only around 1,800 cubic kilometer, out of which only 1,140 cubic kilometer can be put to beneficial use by conventional methods. So this calls for better water management, and groundwater availability is around 450 cubic kilometers. So that is the amount of water that's available to us. And this, I'm just creating a base for the talk. Now, if you see the rainfall pattern also, it is erratic in space as well as in time. This year, interestingly, the India Meteorological Department has predicted that there will be early monsoon. It could start maybe the last week of May, and early withdrawal sometime in the middle of September. The rainfall might stop. So that is a prediction which most of the past 10 years, our forecast has been reasonably good. So we're able to predict, these things well in advance. The average rainfall in the country is around 1,100 millimeters, but it varies from about 11,000 millimeters in the northeast part of the country to about 215 millimeters in the western desert region. That means there's a very, very wide variability of rainfall, annual rainfall in the country. 11,000, it's actually now crossing 11,000 in Meghalaya area, and just about 250 millimeters, the western desert region of Rajasthan, and that is Jaisalmer region is around 250. You can see so around 40 times is the variation. And of this, 75 to 90% rainfall occurs during 25 to 69 rainy days during 4 monsoon months of June to September. That means, though our rainy season is 120 days, 4 months, the number of rainy days is between 25 to 70 in this season. That means the water management in India is very different. There's 60 days of rainfall. You have to store to use for the remaining 300 days. So it's not easy. It's one of the very difficult situations that we have. And you also find the coefficient of variation is more than 20% in most parts of the country. Coefficient of variation is standard deviation by mean, as an expressed percentage. It is more than 20% in most parts of the country. That means so year to year, it changes very, very largely. What happened last year is different from what happened this year, could be what could happen in the future. So this rainfall pattern is also to be understood, and it is very, very complicated rainfall pattern that we have. Now, if you look at the droughts, so that's what I'm going to talk about in the next 1 hour, that some details. about the regions where the drought comes. In Assam region, the drought is very rare, once in 15 years. Assam includes the northeast as well. And you go to West Bengal, you go to Madhya Pradesh, you go to Konkan area, you go to coastal Andhra Pradesh, Maharashtra, Kerala, Bihar, Orissa is on an average once in 5 years. Then you go to the south interior Karnataka, eastern part of Uttar Pradesh, Vidarbha is Nagpur area, Gujarat, eastern Rajasthan, western UP, Tamil Nadu, Kashmir, and the Rayalaseema AP, and the whole of Telangana. The average drought is once in 4 years, and western Rajasthan is once in 2.5 years. That means if you take the whole country, you find the drought periodicity is approximately once in 2 years to once in 15 years, depending on which part of the country we are considering. Now you can look at the global water consumption. Here there are a few maps. The top one is for the whole world, and here for Asia, you got Europe, and the last one, one is in Australia, etc. You find there's amount of water consumption is increasing. This is up to this year, which was prepared, and you also find we use water for lots of other things. So you find that the water consumption has been increasing across the world. Now, if you look at the amount of water quantities available, you find that it's all in square kilometers. You find the fresh water in the rivers, 0.006% of the fresh water available. So you find that the amount of water that we do have is very, very limited. You see here, only 2.5% total available is available in the fresh water. So this is some statistic prepared in the 1978. It's a very beautiful book, Water Balance, the Water is the Earth, and has not changed much. Now we also talk about sustainable development. This is very, very important nowadays in the keeping the hydrologic extremes. Sustainable development is very, very important. Very interesting definition given by Madam Brundtland, who was the Prime Minister of Norway in 1987, the meeting the needs of the present without compromising the ability of the future generation to meet their own needs. It's a very beautiful definition. Now, when you talk about sustainability, we ought to talk about 5 different types of conditions. One is technical, the effective and efficient design and management of resource development projects involving balancing variable demands and supplies. So when you manage water, we have to have an effective, efficient design of the management of the water resource project. We'll talk about demand and supply. Very important. That environmental condition is that there shall not be any long-term irreversible effects. Financial sustainability, the cost of all resource development and management projects must be recoverable. Society must be support and be willing to pay for the services provided by the developmental projects. And we should have institutional mechanism to plan, manage, monitor, and adopt a changing situation, like all of us are part of this. We as academicians and people working in the government departments, both state and central, are all involved in these type of things. So anything that we do must be sustainable with respect to technical, environmental, financial, social, and institutional aspects. Now, when we study hydrology, we try to provide answer to some other questions. What is the maximum probable flood at a proposed dam site? When you talk about water yield, how does it vary in the catchment from season to season and from year to year? This is very important when you talk about hydrological extreme. What's the relation between a catchment surface and groundwater resources? When you evaluate low flow characteristics, what low flow level can be expected to exceed 90% of the time? If given the natural variability of stream flows, what's the appropriate size of an in-stream storage reservoir? What type of hardware and software are needed for real-time flood forecasting and drought analysis? Now, this map was prepared in the year 1999 when we are just entering the millennium. Now, look at this. In the year 1950, you look at this map, the dark color shows that is low amount of water. Light color shows there is there's no problem. So look at 1950, just when India got independence, we are slightly in a lighter color. And 1995, a lot of development took place, population increased, it became darker, and the same trend continues. This year, this has been projected to be in this color, that is dark color here. If I started from Bangladesh to India, to Pakistan, Afghanistan, then the whole Iran, Iraq, etc., the whole Gulf countries, and northern part of Africa is going to have catastrophically low amount of water. Catastrophically low amount of water means less than 1,000 cubic meter per head per year. So this is what is projected in the year 1999, which is not accepted major part of the world. And if I look at the United States, they are okay, slightly better. You go to Australia, is in this color. Okay, so you find that this was the map prepared in the year 1999, which was not accepted by many parts of the world. This map was revised by the International Water Management Institute at Colombo. And you find here that the blue color says there is no water scarcity at all. Now, the whole of the United States, the whole of Russia, most of the part of Europe are having no problem at all. Whereas you look at countries like India, India, China, the northern, the Gulf country, the whole of Africa, the whole of Australia, whole of South America, they are all having problem. The red color shows there is physical water scarcity. That means there is not water available to meet the demand. And the yellow color on the coastal areas, including Australia, say the economic water scarcity. Economic water scarcity means water is available but no money to develop. So this was prepared in the year 2005 by the International Water Management Institute of Sri Lanka. And this was again, there was some issue, many countries not accepting it because Australia comes under this category. But Australia, you find, except the eastern part, many parts are not livable. So they have to redo the map. And this map was, another map was prepared in the year 2013, which is today accepted for most of the development activities across the world. Now look at the map. There is a line here. It says how much water is available in cubic meters. Okay, now for example, look at India. India is in this color. India water stressed to water vulnerability. That means India's water availability is between 1,000 cubic meter per head per year to 2,500 cubic meter per head per year. So you find China, India, Pakistan, Afghanistan, Iran, Iraq, etc. And then many countries here all are water stressed or water vulnerable. And countries in this color, blue color, say there is no water problem at all. The whole of Russia, whole of Japan, many part of Europe, the whole of America, North and South, whole of Australia, and many parts of Europe, Africa, are not going to face problem. There is plenty of water. So this is the map prepared in the year 2013, which is now the basis for most studies that is taking place. Now, just prior to that, another map was prepared. There is plenty of water available. Where is the water stress? Now look at India. If I meet the drinking water supply to everybody in the country at whatever, we have fixed some standard as 135 liters per head per day. If I give water to the whole country, I'm going to have problem for irrigation. That is water going to stress for irrigation. Now the white color shows there's no stress at all anywhere. Even US, you find the western part of US has stress for irrigation. And after meeting domestic irrigation, etc., there is going to be shortage of industry. The red color says, to meet all the demand, there's sort of industry, even in US. And there are some places in the world that we are going to have even water stress for domestic. You find some small areas here and there you find domestic, there's a problem. So this is another map that is prepared, which I think we should understand. Now, let us come to the topic that I'm going to talk about, drought. So drought is a prolonged shortage of water supply, whether atmospheric, that is below average precipitation, surface water, or groundwater. That means this is a general definition that we have. Now this drought can last for months or years, and maybe declare even for a short period of 15 days, like that's happened in our country. It can have substantial impact on ecosystem and agriculture, of the affected region and can harm to the local economy. So drought has a serious issue that it can have on the economy, it can have impact on agriculture, and it can harm the ecosystem of the local region. Now, annual dry season in the tropics is in between the Tropic of Cancer and Tropic of Capricorn, and this significantly increase the chance of drought developing and subsequent bushfires. Like, too much of drought also catches forest fires, and the periods of heat can significantly worsen drought conditions by too much of evaporation of water vapors. That means water gets evaporated too much, there is no water. These are some pictures that I put here. Now, drought can be classified into different categories that I put here. One is the meteorological drought, when the rainfall is much less than the normal annual rainfall. It can be called a hydrological drought when the amount of stream flow is much less than the normal stream flow that you have. Now, which causes loss to the agriculture. It can cause loss to economy. Then you got another loss which is called agriculture drought, when the water is not able to meet the crop water requirement. Now, all this put together can have another type of drought called socio-economic. So these can affect the society, it can affect the economy. So you find another socio-economic drought is also possible. So drought generally can be classified into a meteorological drought depending on the rainfall, a hydrological drought depending on the stream flow, agriculture drought depending on the meeting of crop water requirement, and socio-economic drought, the impact of these drought on the region. So that's how droughts generally can be classified. So you find the impact increase over time, reduced precipitation causes less water into the ground, then you have higher temperature and winds, lower relative humidity, greater sunshine, that causes to increase water loss from plants, land, and ocean. Agriculture drought, reduced soil moisture, crops suffer from reduced yield. This causes hydrological drought, reduced water in the streams and lakes and rivers, and reduced the wildlife gets stressed. All this causes the socio-economic drought. Demand of economic goods exceeds supply, then it affects the community and economy. You find over time these things happen. So meteorological drought cause agriculture drought, cause hydrological drought, and all this can cause socio-economic drought. So that's a drought that we try to understand. So you find the drought characteristics can be classified in terms of duration. How long is the drought going to last? The severity, what is it? How much is the deficit? Then the peak, or the maximum value of the deficit that you have, the intensity of the drought, the spatial, how it is going to spread over time, and the onset and termination. The onset is when the drought is starting and when the drought is ending. Now, if a country like India, you find the onset of monsoon decides, the first monsoon in India comes in the Kerala border. So it depends on the first date of monsoon, the withdrawal of monsoon decides whether the country is having normal annual rainfall or not. For example, the past studies, about 100 years of records of India, rainfall records, show that whenever the first rainfall in Kerala is between 25th of May to 31st of May, the whole country is going to have a normal annual rainfall. If the first rainfall comes after June 10th, the whole country is going to have drought. And the rainfall comes before 25th of May, South India is going to have good rainfall, North India will get less rainfall. This is based on the past record, pure statistics. So the first rainfall Kerala decides when the country is going to have normal monsoon or not. Now this year, IMD has predicted that the monsoon is going to be early, maybe 28th, 29th of May. We might get the first shower. Already some summer showers have started. You find we might have the first rainfall somewhere on 28th or 29th of May, which indicates that the whole country is going to have normal rainfall. It's a very good prediction. Hopefully, it works. Then, what are the effect of drought, adverse effect of drought due to climate change? You find due to deficit rainfall, the higher requirement of irrigation management. That means you need more irrigation, and irregular rainfall, change in temperature has adverse effect on the crop yield, loss in economy. There will be loss in the yield. Then there's going less water storage, lower storage due to decreased flow in river and scanty rainfall. Then the less soil moisture due to less rainfall, lower infiltration, and you have prolonged period of scanty rainfall. Again, less rainfall means that. Then more temperature increases in the evapotranspiration. You find that's how you find all types of effects. You'll find loss in yield, less water storage, less soil moisture, less rainfall, increase in evapotranspiration, more irrigation, and it goes on. So you find there are many negative adverse impacts of drought due to climate change. So these droughts are measured with many indices. You can go to the literature, and depending on the type of drought that we have, depending on the type of data that you have, and depending on the type of studies that you're going to carry out, you can have different types of drought indices. I put an exhaustive list of drought indices. Probably you can in your I'll be sharing this PPT with you in your free time. You can go through and find out which drought index is suitable to your region. So these are many things that we have. Okay, you're fine. You have I classify into the first table is based on meteorology. The second table on the right hand side is based on the hydrology. You find the drought. There are many indices which are being used across the world, and many of these have been tested in India, because India is one country which has got periodically droughts. So we do a lot of work on this in India, and you find every year there's a demand by many states, many districts to declare the districts or states as drought affected to get more funding from the government to take care of the drought. So this is a very common thing that happens, and as people working in drought, we have to give input to the government to help to overcome the adverse impacts of drought. So these are some of the things. Then you also have, earlier I had given meteorology, then you have hydrology. Now, based on the soil moisture, you have certain indices, and of late, geospatial information also gives information on the drought. Using remote sensing, you got a vegetation index, you got a temperature condition index, you got vegetable condition index, and also vegetable health index. Many of these things are from the remote sensing point of view, and you find remote sensing and geospatial technology have changed the way we look at many of these things. In fact, the smart agriculture involves a lot of remote sensing and geospatial techniques. Now, most of the indices that we use, there are some standard drought indices which we commonly use. The standard drought indices, they take into consideration stationary condition where location scale parameters are kept constant. That means we keep the location and scale as constant, and then the standard drought indices, which which in our study we use, are the standard precipitation index, which is called SPI. It represents the deficit of precipitation in the study area, representing meteorological drought. So standard precipitation index is a part of meteorological drought. For SPI, precipitation is considered as the input variable, and the two parameter gamma distributor is fitted to precipitation series with constant local and constant scale parameters. Then you got the standard evaporation, precipitation evaporation index is again an extended form of standard precipitation index, taking into account the evapotranspiration. So here we talk about the water balance value, the evaporation and potential evapotranspiration, and we use the well-known Hargreaves method to calculate potential evapotranspiration. And this is used as input compute the standard precipitation operation index. And so we will see how things are being done. Then another one is the standard stream flow index. So here it represents the deficit of flow in the stream in the steady region. It basically takes care of the hydrological drought. So you find we also fit a log normal distribution to this. Then you got another one is soil moisture index. This is an agricultural drought index. So here again we fit a gamma distribution with constant location, constant scale parameter. Now when you have the drought value, you find some numbers are given here. These are depending on the index that you use. This is one example. Now, depending on the number, the drought can be classified as extremely wet, severely wet, moderately wet, mildly wet, mild drought, moderate drought, severe drought, and extreme drought, depending on the drought index value that you're going to calculate. So, what the various things that I told you, you can calculate and then find out what are the various types of droughts that we can have here. Now, when you talk about drought management, that's very important. When you have drought management, we have to receive the forecast, the early warning and advice from scientific communities and water managers. So for which we need to study the past drought, we do a lot of analysis so that we try to get drought information in advance, which is accurate. So this requires a lot of work and people are working on it. Then we also require information regarding crop characteristics and rotational practices. What are these crops are we growing? Are we using rotational crop? Because the moment drought comes, the land and water management, agriculture practice becomes very important. Then you replace lawn vegetation with native drought tolerant plants. So we have to go for native crops, drought tolerant plants. That's very important. In fact, in our country, unfortunately, we do not go for native crops. We try to get exotic crops from elsewhere and try to grow, but that is not good. Every crop that we choose must be suitable to the local condition, must be local to the total local soil, must be suitable to the local cultural eating habits of the people. So we unfortunately try to bring a lot of non-native plants and grow. That is not good. So we have to go in for native drought tolerant plants. Then for drought management, another thing that is required is we have to have information regarding climate data, soil moisture data, stream flow, groundwater, then the details of a lake and reservoir. Then you have to have develop the key indices and composite drought indices. Then have green infrastructure, porous payments, which is now very common. That we try to have payments which are porous. That means water can enter into the ground, and this can solely stuck in the ground. And ultimately, develop a strong warning system so that farmers could be benefited. Today, there is a lot of things that is happening. That we give drought warning, we suggest the suitable cropping pattern, and we help the farmers. And farmers are also knowledgeable. They demand a lot of things when you do that. Now, for the drought information, there are a few institutions which provide data. Indian Meteorological Department. These give information which can identify the meteorological drought for each state, consider rainfall every year. They give it to, and they have been so successful that they are able to tell well in advance what is the meteorological condition that they're going to have. Then you got the Agricultural Meteorology Department, which gives very kinds of data related to agrometeorological parameters. Then many drought research units developing a pre-harvesting crop prediction model. In fact, most agriculture universities in India, Indian Council of Agricultural Research, they do a lot of this work. Then you have got institutions like Drought Area Study Investigation Circle. They got Center for Research in Drought Areas. Then you got a lot of organizations within the country which have been studying this drought condition. Then we got another center, the Delhi National Center for Medium Research Range Weather Forecasting called NCMRWF. They developed a lot of numerical weather prediction model to medium range weather forecast. And these models are available for us to use in academic area. In fact, interestingly, most data required for any research is available free of cost, provided we give it in writing that this data that we get from the Indian Meteorology Department or from NCMRWF will be used only for research and will not be used for any commercial purpose. So these data are generally given to us without any difficulty. Now, with the climate change, what happens? The effect on the crop development, increase in carbon dioxide concentration, increase in extreme floods, even like floods and drought, and increase in temperature and increase in heat. Some numbers are given here. You find there's an atmospheric impact so much. The gas is almost 80%, radiation comes around 50%, heat is around 60%. So these are various impact on the earth by the climate change that is happening. Now, there are many models which are available now, which are available across, it's available without any cost, it's easily available. Something called a global climate model, GCMs. And in GCMs, we in our studies have taken up coupled model, intercomparison model, CMIP, 3, 5, and 6, phase 3, phase 5, phase 6. And we used 3 RCPs, RCP 2.6. RCP represent concentration pathways, which talks about the greenhouse concentration adopted by the IPCC. So we find they have taken up RCP 2.6 is 2.6 requires carbon dioxide emissions start declining by 2020 and go to zero by 2100. There's one condition. Then RCP 4.5, the representative concept path 4.5, require carbon dioxide emissions start declining by approximately 2045 and reach roughly half of the levels by 2050, level 2050 and by 2100. And then we got RCP 6, emission of peak around 2080 and then decline. And there are a lot of threats. Peak, of course, around 2100. That means 75 years from now, still there will be peak. So these are the 4 conditions that can be used, and these are details available in the 5th annual report, AR15. In fact, recently, AR6 also has been released, which is available free of cost for us to download and work on this. So let us look at the CMIP6 model. And today, this is what is being used. Here, the projected socio-economic global change up to 2100. If you just look at this, the CMIP6 coupled model comparison model, that is what we use. And here we have the shared socio-economic pathways. They have 245, 126, 370, and then 85. These are the 4 shared economic pathways that we use. So if you get SSP 245 means emissions high enough to produce a radiative force of 4.5 watts per meter square in 2100. And SSP 370 means emission high enough to produce radiative of 7 watts per meter square in 21. This is high forcing. Then you got SSP 126. That means radiation up to 1.6 watts per meter square in 2100. This is low forcing. And there's one more which you use 8.5 watts per meter square in 2100. That means we think about 2100 from now, that is 75 years from now, what is the projected socio-economic global changes, and that's what we are seeing. So these 4 models can be used now, and in India these have become very common. We try to use it. Now, when we do the analysis, we also have, because we don't get data for a lot of areas, we have to get some data and try to downscale for our region. We got 2 types of downscaling that can be used. One is called a statistical downscaling. It is based on a view that the regional climate is conditioned by 2 factors: the large-scale circulation, which is well resolved by models, and small-scale features like land use, topography, land use constraint. They're not adequately described by model. That means the large-scale circulation can be modeled well. The short, scale is not described in the model. So we find they try to develop empirical relationship linking large-scale information and local variables is being developed. So statistical study is what we do. Then we have what you call the dynamic downscaling. It's intended to lead this. It's used in the regional climate models and the atmospheric general circulation models, and these are suitable to provide global climate scenario. So there are groups working in our country on both statistical dynamic downscaling and dynamic downscaling. Then you also find when you get the data are biased. So the data must be done some bias correction. So you find the spatial resolution at which the global climate models are run is too coarse to get reliable projections at regional and local scale. So we find we require precipitation and temperature projections at higher spatial resolution for the climate impact assessment. So you can do the bias correction by linear scaling of the precipitation, and then distribution mapping, low intensity scaling of precipitation, and quantile mapping. These are some of the methods available for bias correction. Now, what happens when you have the cumulative effect of drought is the climate, drought, crop yield, all are interrelated. You find a picture here which shows the impact of drought. Now, next 30 minutes, I'm going to talk about one of the work that we have taken up with the three objectives. One is meteorological drought assessment under climate change. Then we talk about non-stationary assessment of drought, and we try to develop drought indices. So these are three objectives that we have taken up, and this has been taken up for the Godavari River. Godavari River is one of the rivers which has been studied by various groups in the country, and so it's easy to compare our results with others because Godavari is one of the most studied thing in the country. So the study area is the Godavari River, which covers. This is one of the largest rivers in the country. In fact, Ganga it could be the biggest, but Ganga, when it starts, Ganga, it's not called Ganga. When it ends, it's not Ganga. The Ganga starts with two tributaries, main, Alaknanda and Bhagirathi, and before joining the sea, it divides into Padma and Hooghly. But this river, Godavari, is completely in India. And so you've got 3,12,810 square kilometers, and it originates at elevation of about 1,100 meters near Nashik and flows over 1,465 kilometers before it enters into the Bay of Bengal. It's one of the longest rivers in the country, covering many, many states. Okay, so the latitude longitude are given here, and it receives 85% of annual rainfall in the southwest monsoon, and the rainfall varies from 600 millimeters to 200 millimeters across here. So you find it covers many states, and there are many small tributaries also here. We got the upper region, then we got middle region. We got Varda, Vainganga is a tributary here. Pranita is a tributary, Manjira is a tributary, Indravati comes from Odisha side. Or ultimately, they all join here. So you find the study area that we taken up is that. So why this river? So we try to find out the problem statement, and this over the years they found that this Godavari sub-basin which you have chosen have been experiencing severe drought periods due to climate variability over the past several decades, and they lie in the rain shadow region of Western Ghats and receives relatively less rainfall. So it's essential to study the drought so that the community's livelihood environment can be improved. So we try to propose an integrated drought monitoring index, take into account the non-stationary behavior of the drought indices. So the framework that we taken up is here. Now you find we try to develop one index here. Then you find construction of multivariate drought index, hazard drought index. Then try to find a correlation between standard yield residual series and SPEI. So you find you can look at these things in your free time. We used a very well-known model called SWAT, and from SWAT is useful to us to develop the construction of the multivariate drought index for future and the reference period. So we did require data for this. So we used a 0.5 into 0.5 degree monthly graded precipitation data, and these data were available for us, which is available to everybody. And we had the data for about 38 years, 2019, 18, 2017. And we got the data, we downloaded from the Indian Institute of Tropical Meteorology Pune website. I give a website here. All this can be downloaded from the regional climatic models. Then the data that we use are the daily precipitation and maximum minimum temperature data. They were downloaded from the IMD website. Then daily precipitation, maximum minimum temperature data for historical period. Then we try to take 2 periods before and after, and then we fought four SSPs, shared pathways I told you, SSP 126, 245, 3785, and they are obtained from the website that I given here, and the source are all here. So then we used to index called Dunn index and seal out coefficient. The Dunn index is the ratio smallest distance between observation, not the same cluster. Like we need to have similar clusters. So we not the same cluster, the largest intrastructure cluster distance. And high D index means better clustering. Number of clusters that maximize D is taken, the optimum number of clusters. Like the whole state is divided number of clusters, try to find what is it. Another one is a seal-out coefficient, that how do you interpret and validate the data within the clusters, how well each subject is classified. So if you have a score of 1 denotes that the data point is very compact within the cluster to which it belongs. So first value is -1, values near 0 denote overlapping clusters. So these are the two indexes that we use. And you find that you find the Godari is in here, and we find the Dunn index values here. You find 4.52 is got the highest, 8.1 is the highest, and corresponding seal-out coefficient also is here, and you find this. So we find based on this, we divide the whole into various climatic divisions. Then we try to the SPI is developed for different climate divisions. This is what we got. We try to compare the historical period with the future time period, and RCP 4.5 and 4.6. So you find that's how that we got here. Climate division 1, 2, 3, 4, 5, 6 here. These are based on this. And we try to compare historical and future drought characteristics. You find here the density and severity here, and you find different colors that we have here for different RCPs. And this we try to understand from the observed period. This actually observed. This is for the future, how it's going to change for different climatic divisions. So some equation that is there. We got the multivariate drought properties. Then we calculate the drought return periods that we can use. And we use some copulas, which are the most common copulas that we can use: Clayton, Frank, Gaussian, Gumbel, and students. These are available literature which you can study. I'm going to do this with you here. Now we found the drought characteristics of SPI computed based on trivariate cupola models. For different conditions, we find these are the values that we have, SPI values. Okay, for RCP 4.5, RCP 8.5. For different return periods, 5, 10, 20, and 50 is what we use here. And this is another T and years of drought characteristics, again for the similar climatic division that we use here. Now the observation that we found here is, overall, the frequency, duration, severity, and peak of droughts are expected to increase in future. That means in the future, we are going to have more frequent drought which is lasts for longer duration, severe, and the peak are going to be more. So the cupola analysis showed that the Gumbel and Frank cupolas performed well for most climate divisions by the two tests that we have. Then you find frequent drought events are observed in the climate division 1, 4, and 6. So you find basically that future we are going to have drought and we have to be prepared to take care of them. Then we try to use another drought index or non-stationary reconnaissance drought index and non-stationary standard precipitation index. The two things are given here. And you find here how the drought propagates from here. You find the drought in the month of January is like this. In May, you find is like this. That means green color says no drought, red color shows extreme drought, the yellow color so extreme, severe, moderate, and no drought. Okay, you find that's how it's going to propagate for two of the indices that we got here. That means it's quite encouraging. And here you find this is temporal. This also the other two indices are on three time scale. This is for NRDI and SRDI, and this is on a 3-month scale. And this is how, for again 2 periods, 2051 to 17, what is going to happen. So find the drought is going to be bad in the future. And we try to use some box diagram here. And you find that this basin Godavari is going to have a lot of drought in the future. So observation that we got here, the temporal drought propagation showed the western parts of the basin are highly susceptible to drought condition in the month of March, April, May, and the drought propagates from eastern to western part of the basin from the month of January to May. It means these 3 March, April, May are going to have severe drought, and severe droughts are higher in the western part of the basin. Then the two models, NSP and RDA, perform better compared to stationary models. The upper Godavari River Basin showed significant influence at various lags. Now we also used two other sub-basins of Godavari, the Indravati and Vainganga. We tried to study the land use, land cover, soil and dam. These are the LULC soil and dam maps. And we try to use this using the SWAT model for runoff generation. So the various two sites we use, Pathagudam and Ashti, we use you find the R squared and NAC are pretty good in these two places. We use here. We use for Indravati River Basin and Vainganga River Basin. And you find climate projections are like this. That means here, the high and low values, you find that this area is going to be highly variable with respect to climate. And you find the temperature are going to be very high in part of the basin. That means the red color shows a high temperature, and the blue color, the red color shows high. 37 is the highest that you get here in different model that we have here. Similarly, mean annual temperature for the Vain and Vainganga and Indravati River Basin are going to be like this. So you find that similarly evapotranspiration stream flow changes also we studied 1976 to 2013, and the future periods you find how the evapotranspiration and change stream flow takes place in the two basins. Then we try to develop the multivariate drought index. You find the green color shows high drought and the red color shows low. So you find many of these places the green colors are very high and low here. Then you want the similar one here for the Vainganga Basin, the first one, and IRB, the second one. So you find there's going to be a high amount of drought. The whole basin is classified as going to have frequent droughts. Now, once we know that these basins are going to be affected by drought, we can start taking care of them right from now by changing the cropping pattern suitably to take care of, to use the crop which are drought resistant. So that's what we have suggested here. So you find the southeastern part of Vainganga River Basin and southern part of Indravati Basin. Indravati Basin comes from Orissa side. They're going to get high annual precipitation, and the annual maximum temperature also showed high precipitation and high temperature in the future. And you also find that because of high precipitation, you find there is a reduction in drought events in the future period. That means Venganga and Indravati are going to be slightly better. So let me stop here with some good quotations for you. This is something I always tell people, can you go 24 hours without complaining about anything? Then watch how things start growing. Then have a lot of positive thoughts every day. And when you work, you come across lots of people. There are people who you like, people who like you, enjoy them. People you like, but people don't like you, accept them. People they like you, but you don't like them, respect them. And people you don't like and they don't like you, avoid them. And in any work that you do, show high amount of integrity, motivation, honesty, innovation, sincere hard work, and leadership. And let me stop here. This is a you have my email ID here. In case you would like to ask any question, please do not hesitate to mail me. I'll give a reply within 24 hours if I'm free. And this is another picture which has developed a lake in Kerala which was purified without using any chemicals and pump and power. And that's a plant that we use to purify the water. The water we purified up to 90%. Thank you.
Thank you, sir, for a wonderful presentation and sir giving a lecture on drought and various different aspects, as well as sir, some of the very interesting slides in the last, so that we can motivate in the research and teaching professions as well. I would request, if somebody has any questions, please ask. If you have any questions, you can ask now. Interact with sir.
Question may be less because there are too much things covered in 1 hour.
Yes, sir.
But
Yes,
I
sir.
will share the PPT with you.
Sure, sir.
The
Sure, sir.
students can go through it at their free time, and then they can mail me their difficulties. I will answer them.
Any questions, please? Okay. Somelji, over to you.
Yeah. So, okay. Thank you so much, sir, for such a wonderful talk. We have learned many things in the drought, and how do we calculate, from the different index as well, from the different data sets, from the different, climate models. I hope students have also learned many things from this presentation. And if they have any questions, they will, sir, interact with you. I am very sincerely thankful to you, sir. Thank you so
I
much
will
for this
share the
talk.
PPT with you just now, Praveen. So
Yeah.
I'll send it to your email ID.
Sure, sir. Sure, sir. Sure, sure, sir. I'll share with them this presentation to everyone. Yes.
Thank you so much.
Thank you so much, sir. Thank you so much.
Thank you, sir. Thank you. Thank you.
vehicle.
आज की तारीख में हो जाएगा फ्री टाइम में।
It wasn't on? It's not? Oh, yeah, okay. Yeah. So say it's so this one I don't. Like this? Yeah. It's good. All right. Good afternoon, everyone. Hopefully you have a good lunch. Any questions for the material we discussed in the morning? Any questions before we continue? Okay. All right. So yeah, I guess in the morning we basically talk about what is IPCC, right? So what do they do, and what's the history of IPCC, and then we talk about some basic concepts of climate science. What is basic concept about climate change, right? So why we use anomaly, right? Not absolute observations, right? Why we care about the uncertainty, how IPCC deal with uncertainty, right? So what is CMIP, right? What's CMIP 6, things like that, right? So then we'll, in the afternoon, we'll continue to talk about some of the key IPCC findings, right? So like mentioned, the whole report is more than 2,000 pages. So we won't be able to, cover all of them. We can just pick a very small proportion, I think quite important and quite relevant to us. So again, this is IPCC report, the first chapter. So for this lecture, we'll basically talk about what are the major drivers in our climate system and how do we know them. What other ways people measure the changes. And when we think about the Earth's energy balance, right? So the two important things, the Earth, the source of the energy is actually from sun, right? From the solar energy, right? So that's why when we think about the changing climate, we have to think about whether the source is changing, whether solar radiation is changing. And also we talk about positive and negative radiative forcing, right? So for the greenhouse gases, their radiative forcing is positive, but there is one big player in our Earth's energy system, that's volcano forcing. So that one is a negative radiative forcing. That means they are cooling the climate, right? So when we think about the changing climate, we have to think about how solar energy has been changing and also how volcano activities has been changing in the past. So this is from IPCC report. On the left, we are talking about the solar radiation change. In the top one is in the last 2,500 years, and then the bottom one is the last 150 years, more recent change. And on the right panel is basically, we are talking about the volcano forcing. On the top, again, is the long-term trend. We are talking about the 2,500 years. And then the bottom is about 150 years. So let's look at the left one first. That's solar radiation, right? What's the general trend you will see in the last 2,000 years and the last 150 years? Is increasing or decreasing or no change? We're talking about this one. It's not a tricky question, right? So we're just reading from the figure. You're talking about here, right?
In 1900, it's constant. Then it is increasing. Then again, 1900 it's increasing.
Okay.
Constant.
Right. So yeah, if you look at the 2,500 years, right? So it's relatively stable, right? So there's not a huge change. But when you look at the last 150 years, there is a slight increase here. But when you put into the context of the long-term history, you will see the change is actually not huge. Even it looks like there is an increase. But when you put this part of the increasing trend into the 2,000 years, there are times like that magnitude, right? So that is IPCC conclusion, right? So basically, in the last 150 years also, yes, they're a little bit higher compared to maybe here. But when you put into the longer context, it's not like a huge change. So that's basically the IPCC conclusion we have about the major driving force of our climate system, right? So that is the ultimate source of energy for Earth, right? So essentially we are talking about, essentially they are quite flat, no huge change. How about the volcano activity? What?
I just want to know about the figure A. If you look at the scale of the violence, it seems very small.
Right, yeah. So you mean the changes are very small, right? Yeah.
Then can it be attributed to some errors? I mean, we are measuring something, we are measuring the indicator, right? Some senses or some observed data, and then we are plotting it. So the scale on the y-axis is very small. So what about the stability of that data? And will that be error free?
Right, that's a good question. Yeah, so basically we are talking about the number, the change in number is very small, whether we can make good enough measurement, right? So yeah, that's a good question, right? So that's basically, right now what we are measuring is using satellite, from, we can directly measure the radiation outside the Earth without influence of Earth's like atmosphere, right? So it's very accurate. We know that. And but when we talk about the 2,000 years, really you actually use a proxy, right? You use not direct measurement. You are right. So there's some uncertainty in terms of the proxy. But again, people try to use the same proxy and then calibrate that with the most current, 30 years, 40 years measurement, and you can see the calibration is very good, even with a small number, because they don't, energy measurement is not that hard, just like temperature, right? So it's actually, you could measure them quite accurately. So, but you are right, we are really talking about a very small change, right? But again, that's a point, really the change we are talking about, you can say is really less than like 1 watts per square meter, right? Out of 1,300 watts per square meter, right? It's relatively small. So how about the volcano forcing? What's the general trend? Is it increasing, decreasing, or no obvious trend? So remember this one we talk about, that is only negative forcing, really major negative forcing in our Earth system, like a cooling Earth essentially. So what's the trend tell us in general? Increasing, decreasing, no trend? So this is what IPCC put, right? So I guess, in summary, essentially we are talking about, there are basically variability, but there is no like obvious like increasing or decreasing trend. It's basically in the last 2,000 years, it has been relatively stable, right? So because volcano activities, as we know it, is random events, it's not like there are like a frequency we can describe, right? So in the last like 150 years, sometimes there are big ones, like we talk about, the one in Philippines, right, 1997, right? So it's a big one that's cooled the Earth's temperature for almost a year, right? So that does impact Earth system, but Earth system like energy balance. But when you look at the long-term trend, there's no like a clear trend. So I guess really the key message here is when we talk about climate change, right? So what's really driving climate change is not from solar activity, it's not from volcano activity, right? So that's really the key message. So really what happens, we know, is what happens in the Earth's atmosphere, right? The greenhouse gas are changing. That's actually the major cause of our temperature change. So when we think about the greenhouse gas in our atmosphere, right? So Earth has a long history, right? So it's actually there are different periods. There are actually Earth has a very high CO2 concentration, much higher than what we have now, right? So we'll look at 3 figures, like 3 pages of Earth's history in terms of greenhouse gas. This page we will see like a deep time, right? Geological time. You can see it's 450 million years old, right? So we talk about really like ancient time. We zoom in to like the recent 60 million years, and then we zoom in to the last about 3 million years, right? So that's what look like. So this one, of course, you can imagine that's not direct measurement, right? So we don't have a CO2 number, from that time. So what people does is actually using the geochemical process, right? So that's called a foraminifer, right? So that's a small living creature lived in the ocean, right? So their shell is a carbonate. So carbonate has oxygen. Oxygen exchange with CO2. So you can actually refer to the CO2 concentration, right? So people collect them. They are very small. You can't really see them from naked eye. You have to use a microscope, blow up, and you'll be able to see them. So people use this type of a chemical tracer to be able to refer what CO2 level in Earth has been in the deep time, right? So you can say essentially there are periods we have a very high CO2 level, but in general what we saw here is from around 60 million years old, Earth's CO2 level has been dramatically decreasing, right? So that's really the overall trend, right? So Earth has spikes, but in the last about 60 million years, the CO2 level has been slowly declined, right? And then when we move to more recent history, right? So we are talking about less than a million years old. So these are the almost direct measurement, right? So these are the ice core measurement, right? So basically, you have the gas trapped into the ice core, in Antarctic, and also in some glaciers. So people can, extract air out and then measure the three major greenhouse gas directly from ice cores. Right? So that is a direct measurement of the concentration of greenhouse gas in last 800,000 years, about a million years. Right? So basically what we saw here, there is a fluctuation of all three gases. Right? So that is basically the glacial and deglacial cycles. Earth has many of these cycles, right? But in general, it's also stable, right? In last million years, the greenhouse gas concentration has been stable. Really, what happened is in the last 150 years, since the start of industrialization, right? Since we start making use fossil fuel intensively for our industry purpose, life purpose. So CO2 and methane N2O has been dramatic increase. Right? So that is ice core measurement, more recent history. And then we have a more direct measurement, right? So really just the modern measurement, really we measure exactly how much the concentration. So again, even this one is kind of a direct measurement, but you actually measure from the air bubbles, right, in the ice core. And this one is actually directly measure the CO2 concentration in the atmosphere, right? So these are so we will talk about each individual one separately. But here I just give you the major sources of different measurements. So the key message here is there are different groups in the world. They actually directly measure this CO2 gas or this greenhouse gas, right? So there, for example, the first one is you don't need to remember the acronym, but essentially that's NASA, the agency of NASA. They basically measure greenhouse gas. So another major one is from NOAA. So NOAA has a global network. They try to measure the greenhouse gas. When I do field work in Africa, I remember that's one very remote research station in Namibia. So they actually help NOAA. They are one of the NOAA monitoring site. Every month, people actually drive the car deep into the desert, use flags from NOAA and fill the air and then ship to NOAA. NOAA will measure this. So these are NASA or NOAA is kind of a government-sponsored program. They try to continue measure greenhouse concentration in the air. And then there are some university ones. One is from University of California, San Diego. Right? So that's from Scripps Institute of Oceanography. Right? So that's is famous for their oceanography program worldwide. So they keep measurement of greenhouse gas as a global scale. Another one is from University of California, Irvine, UCI. So from their Department of Chemistry, they have a program has been continuous running the greenhouse gas in the air. Right? So there, basically the idea is, so that's are the major sources of IPCC report. Where they get the data from is from these different sources. Right? So in the map actually is showing the different sources. You can see they almost matching each other. Right? So give us confidence. Some are government-sponsored programs, some are just the university-sponsored program. So they give you similar answers. So we'll talk about three major greenhouse gases separately. Right? So the most major player we know, of course, is the CO2. Right? So that is a major reason for our Earth's temperature has been increasing. Right? So the CO2 measurement the early start is from 1960s. I think 58 is the year really start. Is in this location. So everybody know where this one is? So it's in Hawaii. It's Mauna Loa. That is the start of the global CO2 measurement. Right? So that is from 1958. Right? So is a scientist, Dr. Kalim, right? So later you may heard of a Kalim curve, right? So that's the name after him because he initiated this program. This is a relatively remote island, far from major industrial sources. So that's why the data from here will be used as a kind of a global representative numbers, right? So since 1960s, the measurement has been continued on. Right? So that's you can say that's unfortunately the number has been continually increasing. Right? We already passed 400 mark in 2000-ish, and right now we are around 410-ish. And in this insert, so this one is a derivative. So that is basically the first difference between this year's number from last year's number. You get the rate of change, right? So this is overall concentration change, and this is the rate of change. So you taking the difference between this year's number from last year's number. So two quick questions. What responsible for the zigzag? Why CO2 has this zigzag? What's the major reason for this? So when you have a peak here, that means that is the highest CO2 level within a year, right? Why that happens? So you can see the zigzag is annual trend. Every year you have a peak, so you have a valley. Yeah, it's a seasonal activity. What seasonal activity? Say that again. What? You mean human activity? Okay. So the zigzag is actually not human activity. It's not like, for example, some may think in winter you use a lot of heating, maybe you generate a lot of CO2, right? So sure, that's play a role, but not a major reason for this. It's not big enough. Any other guys are thinking? Did you try to say? So what's the major reason you said? Vegetation. Okay. Yeah. So yeah, that's exactly right. So when you think about the global carbon budget, right, how much carbon we emit, right? So like about 1/3 of that emission is actually taken up by vegetation. So they are actually the major player in terms of carbon sink. They take up that 1/3. Then another third is taken up by ocean, right? The ocean take another 1/3. And then the leftover 1/3 is basically used to increase our CO2 level, right? So that's basically the rough budget. And ocean really doesn't change that much in terms of their kind of seasonal carbon uptake. Really what happens here is the zigzag is the vegetation, right? So, basically if you have a winter time, vegetation stop taking up CO2, stop photosynthesis. So you have a peak there. And then, during the summertime, the valley basically means the vegetation has been very active during the peak summertime. They take up a lot of CO2 from the atmosphere. And then you have a valley here. So every year you have a peak and a valley because vegetation either active doing photosynthesis or don't, right? So that's why this zigzag happening. So yeah, it's because of vegetation, because of photosynthesis. And another thing is you can say we are not only the overall trend is increasing, the rate of increase, the ppm per year is actually still increasing, right? So that's actually kind of alarming, right? So it's not only that means, if this one is not zero, if the rate is not zero, that means the curve is always up. But if the rate is actually still, you still produce more and more CO2 per year. So that means the curve will be kind of exponential increase. So that's actually the problem we are facing right now. Right. So another question for you guys is you notice, right, for later, like for all the greenhouse gas, we use a ppm, or ppb, part per billion, or even part per trillion, depends on the different greenhouse we talk. Like for methane and N2O, we'll use ppb, and for some trace gas, we use a ppt, even small, right? But whatever the unit we use is based on dry air base, right? So all the numbers you are reading here is the dry air based numbers. So why we use dry air base? What do you think is the reason we use the dry air rather than wet air? So yeah, why we use like a dry air based measurement for all the greenhouse gas measurement? You want to say something? So yeah, you are getting there. So you are talking about, like try to produce the ideal condition density for like greenhouse gas measurement, right? But it is on the right track. But think about the dry air. What dry air means? What we get rid of? Water, right? Water vapor, right? So that's basically dry air mean, right? So why we use dry air? Because water vapor is actually a big component of our atmosphere, right? So it's actually, when you think about the CO2 ppm, right? So water vapor is probably like 1,000 ppm. It's actually very large number. But at the same time, it's actually variable. It's not everywhere you have the same water vapor concentration, right? It's quite variable, right? So if you don't get rid of them, your number will be get affected, right? So that's why we always get rid of water vapor from the greenhouse gas measurement, right? So because water vapor has a high concentration in the air, but also is spatially variable, right? So that's why you have to get rid of them before you make a measurement. So that is CO2. And the next powerful greenhouse gas is methane, right? So that's very similar in terms of the trend. So you can say methane is not having the zigzag, right? It's essentially, we'll see, methane has been level off for some years and then is picking up again, right? So far, compared to CO2 and N2O, methane has a larger uncertainty, right? So just because it has a lot of source and sink, we still try to understand that, handle that better. But in general, we know methane has been increasing quite dramatically. And also, when you look at the insert, that is the rate of a change. So what this number tell us? I guess in terms of rate of change. So what's your conclusion you will get if you read a figure like this? So again, remember we talk about as long as the rate of increase is not zero, the curve will be increasing, right? So you can say methane, most of the years essentially the rate is above zero, right? So that means even the rate didn't change too much, it's more or less stable, right? But the rate is not zero. That means for sure we will see the methane concentration in the air will continue increase in the future. Right? So here is a figure from a global methane budget is from program called is a carbon program. Try to have idea for the methane on Earth where they are. Give us idea. But this one you can see actually there is a very large range for a lot of the process, right? So there is uncertainty is quite big. People still try to narrow down the process. So, but in general, basically this one, for the green ones, talking about the natural process, and the kind of orange color is more like a human activity, anthropogenic activity. You can see some agricultural waste is a big producer, and fossil fuel production from industry is also layer. But for methane, has a lot of the natural process. So the big one, the big sink is actually from chemical reaction in the air, but there are some other like natural resources from wetland, right? Wetland emission, and there are some from the agriculture like rice production. So I guess really just to give you an idea what are the relative players in terms of the methane production and the methane sink. Methane sink is really, the big one is actually from a chemical reaction, right? Very different from CO2, right? CO2 is the major sink is from vegetation, is from biological process. So it's different. So, but people still try to narrow down the uncertainty, try to get this number. It's still very active research for methane budget. So the number 3 major greenhouse gas is N2O. So what's the general trend for N2O in terms of overall concentration and also the growth rate, from the insert? What's the general trend here? It's not a tricky question. Yeah, just. Anybody want to? Increasing, decreasing, stable?
Increasing. Gradient is increasing. Gradient is constant, so concentration is increasing.
Okay. So, yeah, so basically, that's a pretty obvious, like an increasing trend, right? So, but also for methane, for N2O, the rate is not zero, it's above zero, right? So that means, is for sure will increase, but also there is a slight increase in the rate as well. So that means, it's increasing, but it's actually even up. It's not like a linear increase. It's actually the rate will be faster and faster, like similar to CO2, right? So that's. So what's the major source of N2O? Anybody know? What's the number one source of N2O in our atmosphere? Can you speak louder? Okay, so you talk about industry. Actually, for N2O, the major player is agriculture. So the largest producer of N2O is actually from agriculture. So that is the largest producer. So that's why, people try to develop different ways to try to reduce N2O emission from agriculture. Right? So that agriculture is the largest producer. So can you guys hear me okay? Okay. So far we talked about the three, like CO2, methane, and N2O. There are three major greenhouse gases, right? But in our atmosphere, there are actually some minor ones. Their radiative forcing is actually much more powerful than the CO2 or methane or N2O. but because they are trace amount, so we don't talk about them a lot, but they are actually very powerful. So you can see we are using the unit of ppt, that's a part per trillion, right? So remember, when we talk about the methane, that's a ppb, part per billion, right? And the same for methane. Methane and N2O is a part ppb, and CO2 is a ppm, and for them is a ppt, right? Part per trillion. It's a very minor like a component, but we still care about them because so this our group called hydrogen native greenhouse gases, right? So basically, when you look at the element tables, right? So they are really from the halogen column, all of these gases, right? So the most famous one is the CFC, right? So that's one, the famous fault, they can destroy ozone in our atmosphere, but at the same time, it's actually a very strong greenhouse gas as well, right? So people use them for use for refrigerator, right? So as a coolant and the other things. So it's purely man-made, right? So it's not like naturally occurring, but people made this chemical to use for our purpose, and they realize it's actually become a very powerful greenhouse gas. So that's why people, and also this one, CFC is a carbon fluoride. So the fluoride part is very powerful, destroy like ozone layers, right? So that's why people try to eliminate them from atmosphere, right? And these two gases are the replacement for CFC, right? So that's why you can see CFC is actually level off, even like going down. But for HCFC and HFC, they are increasing because they are the replacement of a CFC. So I guess they are minor in terms of concentration, but because per molecular basis, they are very, very powerful. That's why right now people consider them as well. So for some other trace gas, we don't talk them too much, but they are actually used for like computer chips and other things. They're actually quite, you can imagine with modern technology, people rely on them a lot, and these gases exponentially increasing, right? So right now, their concentration is relatively small, but they are very powerful greenhouse gas. So that's why people care about them. So for the CFC, that's actually the decrease is caused by the Montreal protocol, right? So to me, that is a kind of a successful story of environmental science, right? So that's we figure out the problem. We know CFC has been destroying ozone layers, and people then getting together, they signed the protocol, Montreal protocol, right? So they basically talking about, okay, we stop doing CFC, right? We find other chemicals like for the same purpose, and that's actually making the CFC lower, right? So that's actually a successful story. So like we talk about CFC, because the ozone, right? The ozone is itself is also greenhouse gas, but at the same time, ozone, depends on where they are, right? So there are two major types of ozone layers. One ozone layer is in the stratosphere, and one ozone layer is a kind of man-made, is in troposphere, right? So for the stratosphere ozone, right, we typically use the Dobson unit, right? Dobson unit, we are talking about under standard temperature pressure, you have a 0.01 milliliter, that is one Dobson unit. Essentially, we are talking about, essentially 1 milliliter is equivalent to 100 Dobson unit. So here, I give you a scale, right? In US, if you have a penny, right? So if you have two penny stacked together, that is a 3 milliliter. That is the average depth of ozone layer in our atmosphere. So that is a good ozone layer. That is the one really helping us, right? Because ozone actually causes skin cancer, right? So they actually helping us for that. So this is from IPCC report talking about the ozone layer trend in recent years. So here is a global average, and then you have the kind of the different zone, different climate region, northern atmosphere, tropical region, and you have a southern atmosphere, right? And then polar region, right? So you can see their scale is slightly different, right? But it's around 300 Dobson unit. So that is a natural concentration for ozone. And you can see for northern atmosphere and the tropical ozone layer wasn't changed too much. Really what happens the most is the southern atmosphere and the polar region. Ozone layer has been depleting very fast in the last 20, 30 years until recently becoming stabilized. Right? So that's because of the Montreal Protocol. So because we got rid of the CFC from our air. Right? So here just give you an idea for like UV layers. There are 3 types, right? UVA, UVB, and UVC. Right? So they have different wavelengths, and basically the shorter the wavelengths, the more energetic they are. Right? For UVC and UVB and UVC, they are the really dangerous one, very energetic. Right? So ozone essentially can block most of the UVB and UVC, right? Only like UVA can go through, right? So that's why is less energetic, less harmful for us. So that's why the stratosphere ozone is very important. But again, like we talked about, for ozone, not only we have a stratosphere ozone, we actually human activity also create a troposphere ozone. Right? So that is a kind of a 2 story of ozone. One is a good one is a bad one. Right? So that is a surface ozone or troposphere ozone. Right? So the x-axis is basically the trend, y-axis is latitude. So the trend basically we are talking about the kind of per decade whether they are increasing or decreasing. Right? So based on this, so these are the kind of ground measurement. These are the satellite measurement. And in more recent years, people have a satellite measurement for surface ozone. So again, ozone is a pollutant, right? It's man-made, based on essentially from if you go to gas station, right? If you have a VOC come from the gas pump, if you are under a sunny condition, then you have a NOx coming from the pipe from your car. So it's a perfect condition, they will create ozone, right? So that's a ground level ozone. It's a pollutant. If you have breathing issues, asthma, for example, it's very bad for your health. So that's why people monitor them, monitor the changes. So based on this type of measurement, what's the general conclusion? Like the ground level ozone is increasing or decreasing in recent decade? So again, all these figures are from IPCC report. I put the number here, right? So that's typically referred to the chapter number and then where they are. If you want to go back to read the chapter. So, but one of the idea is that you should be able to, read their figures, try to guide what's kind of a major trend. So, based on this type of figure, right? So for the surface ozone in the recent decade is increasing or decreasing? It's not, so it's not tricky, right? So, you'll see there is a 0 line here, right? So, basically if the number is on the 0 line, on the left, negative, that means, the trend is decreasing, and if on the right, right, it's increasing, right? So basically what this one tells us, right, especially in the lower latitude, right, from, you can hear in northern atmosphere, that's the most industrial activity happens, right? So you can say it's actually the ozone concentration has been increasing in recent decades. So you can see here too, and that is also reflected in the satellite measurement. So there are some places that are decreasing, but for majority of the measurement people have is actually increasing. Right? So that's essentially this message tell us. Right? So in recent decade, the ground level ozone has been increasing. Right? So that's not good news for us, right? Because it's a pollutant is actually affecting humans' health. Right? So that is a man-made ozone. So that's quite different from the stratosphere ozone. That's a naturally occurring ozone. That's actually protect us from the UV radiation. Right? Any questions? Okay. So I guess the key point is make sure you understand there are two types of ozone in our atmosphere, right? So the lower level, like a troposphere ozone, right? So how high is the troposphere roughly? I heard the number. 10 kilometers, right? So that is really kind of a rough height of a troposphere, right? So basically all the weather events, the storms, things happen within troposphere, right? So that's why airplane will fly above that, right? So you fly above 10 kilometers, right? So, so the troposphere ozone, right? So that's bad. That's a man-made ozone essentially, right? But another type of ozone is naturally occurring. That's in way above 10 kilometers, right? That's a stratosphere ozone, right? So that's good for us. That's actually protecting us. So the other things in terms of atmosphere chemistry, like changing the climate drivers, would be the aerosol. Right? So here we talk about aerosol. We talk about that is non-sea salt sulfate and also black carbon. Right? So essentially they are the industrial production. Right? So either black carbon or the sulfate is from industrial activities. So here are some basically satellite-based measurements, and they are the spatial average. So what's the general trend you can see in terms of the aerosol in the atmosphere? So there are regional differences. But in general, what's the general trend what's a major conclusion you can get? So again, it's not you can say like there are like different regions, right? So that's represented by different color, and then we talk about in the last 150 years. So there are different information there, but what kind of information you can get from this? Anybody want to try? Just describe what you found from the. You want to say something? So is that all increasing or decreasing? Oh, there. I guess basically you can say, right, so depends on where you are, right? So some regions you can say is actually continue increase. Some actually increasing and then start decreasing, right? So I guess you can pick the region, but the idea is essentially for the like Europe, like for North America, right? So it's actually they are on the similar trend. So they has been increasing dramatically until maybe 1980s, and then there will be sharp decline. So the same, you can say the Europe like this, and Greenland is affected by Europe as well, right? So Eastern Europe like this. So essentially for the industrial world, right, or Western world, so historically there has been very dramatic increase in their aerosols because of all the industrial activities. But in recent years, they have a sharp decline, right? So, but the pattern is different for developing country, right? So here you have South America. Yeah, somehow for this report, like East Asia is not here. Actually, East Asia is very similar, like India here, like China is actually all similar to South America. It's actually still like a sharply like an increase, right? Just because of the industrial activity is quite strong, and the environmental regulation is not as strict as in Europe, right? So, you can, if you look at the global map, you can actually see that, right? So that's in the last 20 years, right? From 2000 to 2019, you can see for like US, for like Europe, right? So it's a green, right? So that means their aerosol, that is aerosol optical depth, right? When you look at from the satellite, from space, like all the way through the column, so you can see is actually decreasing. But when you look at East Asia, right, here, India and part of Africa, you can see they actually still on the increasing trend, right? So there are actually regional differences essentially, right? So if you, some part of the world is actually still continue increasing, but many other part is actually increasing and then stop and decreasing quite dramatically. So, one of the major reasons for this decrease is actually through the environmental regulation, right? So, in US and in Europe, right? So from the 70s, they actually pass the Clean Air Act, right? So that's first started in 1970, and then there is an amendment 1990. So it's very similar for Europe as well. So they actually passed similar type of law, and this law, two things are very relevant to the aerosol. One is a mandate for all the cars; they have to equip with some of catalytic converters, right? So that's why you can actually convert all the carbon monoxide to and hydrocarbon to carbon dioxide, right? So that's why it's more from the public health point of view. You don't get poisoned by carbon monoxide, right? If the combustion is not complete, you will have the issue with the carbon monoxide production. So that's one of the mandate from the Clean Air Act. So another one more relevant to like aerosol reduction is actually for the power factory or for the anyone use smoke stacks. So one of the requirements for them is after they burning things, they have to basically install the scrubber, like things like this. So the idea is they use carbonate calcium, right? So that's react with sulfur gases and then produce gypsum, right? So that's basically the material of the walls, dry walls, right? So that's a gypsum, right? So the idea is they go through a serial process. They settle down the gas, like the big particle already settled down, and then the leftover will actually passing through a scrubber to be able to get rid of all the sulfate aerosol. So that's become very effective, right? So that's why we talk about in Europe and in US. So essentially there is a huge reduction in the aerosol, right? So that's it's very good for the human health point of view. Right? So that is the main reason for the big reduction in recent years. Any questions so far? Okay, so far what we talk about here right now is really talk about kind of the drivers, right? So we talk about, you know, the solar activity, the volcano activities. They are not really the major driver, right, for the observed warming, right? Really, the observed warming is through the greenhouse gases we produce, right? So the major player is CO2, but methane, N2O, and the halogen gases, they all responsible for the greenhouse warming. Ozone is also a very important player as well. Right? So aerosol, again, that is the only major cooling force in atmosphere. Right? So that one, you know, essentially there are regional differences. Right? So some places are decreasing, some places still increasing. Right? But we can't rely on aerosol to cool our climate because, you know, even they are cooling the climate, but they are not good for our health, right? So it's not good for our breathing, right? So, you know, that is a problem. You can't rely on them, even they are cooling, right? So far, you know, what we talked is really the drivers of climate change. And then next few slides, we will touch on is basically we'll talk about the kind of the trend, overall trend, right? So what the Earth's temperature look like and the detailed information about that. So, you know, this is a figure from IPCC report. So, you know, that is a kind of the Earth's temperature in deep time, right? So deep time we are talking about 60 million years old, right? So remember, when we talk about CO2 concentration in deep time, that is a time when CO2 concentration has been declined, right? So you can say, you know, even without, you know, you can actually have a good mental linkage between CO2 concentration and the temperature trend in our Earth's history, right? When CO2 concentration has been declined, Earth's temperature has actually been declined quite fast. And also, this one is pretty interesting, like give us kind of the brief history of different things, right? For example, when agriculture started, right? You know, about maybe 10,000 years ago, right? So that's agriculture time scale. And then when we think about ice sheets, right? So ice sheets is really the largest ice on Earth. That's only appear in Antarctic and in Greenland. Only two places has ice sheet. Right? So, you know, you can say, give you the time scale of ice, where ice sheet actually start, right? Ice sheet is start like about 30 million years ago, right? So that's East Antarctic ice sheet, and the West Antarctic even later, right? So that's tell you like how old the ice sheets on Earth. So, you know, just to give you kind of you know, that's when humans as a species actually start, right? So that's give you a relative time scale, like when agriculture start, when ice sheets on Earth start, and how the relative change was in general the trend of a temperature. You can say like in the Earth's history, right? So there are times much warmer than what we have right now, right? So we're talking about 15 degrees C, like above the you know, the pre-industrial period. But remember, that's very different time, right? So there's no human on Earth, you know, there's not even ice sheet on Earth, right? So it's very different. So that's just give you a kind of a perspective from deep time, how Earth's temperature has been evolved. And for modern time, right? So when we talk about surface temperature, so the idea is there are two different ways. You know, when you read literature, you probably heard GMST or GSAT, right? You need to know, okay, what they actually talking about, right? So GMST is actually referred to global mean surface temperature, and GSAT is a global surface air temperature. And so really, you can say the difference is one is called global surface temperature, one is called global air temperature, right? So the main difference between these two is really the ocean part. And for both data set, people use the land surface air temperature, SLAT, right? So these are the same between these two. Really, the difference is how people measure ocean temperature. Right? One of the data set, people will measure sea surface temperature, SST. Right? For another one, people use marine air temperature, M80, right? So this is surface temperature, this is air temperature, right? So they are different, right? So you know, like if you go to desert, right? So the air temperature may be like 40 degree, but if your bare hand, touch the sand, you know that's 70, 80 degree, right? So there's actually huge difference between air temperature and the surface temperature, right? But for ocean, the difference is not that big, but there's still a difference there. So, but that's why we have two type of data set. Like when we talk about the global temperature change, some people use surface temperature, some use global surface air temperature, right? So, but when you look at, again, just like anomaly, right? Like when we think about the trend, regardless whether you use, some use GMST, some use GS80, when you compare the change between different periods, what kind of conclusion you can get here? So I'm talking about this table. So, that's we are talking about different period, right? You compare these two period or these two period, and then how temperature has been changing based on different data set. What's a general conclusion you can get from this comparison? So for the trend between global mean air temperature or global mean surface temperature, when we look at the trend, are they same or are they different? So if I use, for example, global mean surface temperature to calculate the kind of the trend or the change in different period, compared to if I use a different data set, if I use global surface air temperature, whether I will get the same conclusion or not. Based on this, what's your conclusion? So I heard same. Same? Say that again. Same, right? So, yeah, I mean, this is the same, right? So, like we mentioned, the temperature itself could be different, right? So, air temperature, surface temperature, and air temperature, they could different, right? So, but when you look at the comparison between these two, that's changes, right? So they almost spot on, like almost exactly the same. So basically, when we talk about the change, it doesn't matter which data set you use. It actually give you the same conclusion. So again, like anomaly. If you use a different thermometer, right? So maybe the absolute number is different. This thermometer maybe give you a little bit higher number. This give you a lower number, right? So, when you compare these two numbers, sure they are different. But when you use this same thermometer, you measure the same thing, like time by time again. You look at the difference, the change. They are same because the difference cancel out, right? So the same idea for the two data set, right? So you can use any data set for calculating the trend. That's give you confidence to show, okay, I can use any. It's actually give me the same trend. Give us confidence about the trend we observe, right? So that's a good thing. And this one is a kind of surface temperature trend, right? So this is from 1900 to 1980. And this one from 1981 to 2022. So that's a global temperature change. What major conclusion you can get, when you compare these two? In general, anything like come up in terms of spatial distribution? What's the kind of the take-home message you can get from this? There are a couple of things, right? Very. Can you say that again? I didn't. Oh, sorry. Yes, there are significant changes. Yes. So I guess more specific, if you compare these two maps, or like talk about one map, what kind of the features you can comment on? So maybe let's say spatially, what kind of a major conclusion you can get? So I guess your point is almost like everywhere is warming, right? So that is a major conclusion. Yeah, that's one key message you can get from this. But there are other information here, right? What other information you can get? Variability. Oh, okay, yeah. So the other is the spatial variability, right? So you can say polar region actually warming much faster, right? So the rate is much faster. They actually got impacted much significant than other region. Yeah, that's a very important message here, right? So they sometimes people call them like vulnerable regions, right? So yeah, that's definitely. What else? I guess if you compare these two, right? So that's a different period, right? From 1900 to 1980, right? So that's they are using the same scale of change. What that tell you? Right, the rate has been accelerated, right? So you can see here we're talking about 80 years of change, and here is only like 40 years. And but the changes we saw here is already bigger than the 40 years of change, already much bigger than the 80 years of change, right? So the rate has been accelerating much faster. Anthropogenic activity. Yeah, I mean, you're talking about the reason why that happens, right? So yeah, essentially, yeah, exactly. That's pretty much all the greenhouse gas emission we produce. We talk about the CO2 growth rate has been accelerating, right? The growth rate not only not zero, is actually accelerating, right? So that's really the major reason responsible for the kind of the faster change, right? So yeah, again, yeah, there are a couple of important messages you can get, right? So the rate of change is accelerating, and also, there are spatial variability, right? The polar region actually got affected much more severe than other region, right? And also, like a spatial variability, but also time variability, right? So yeah, I guess that's what we know in terms of a global distribution. And if we average them together, right, like average all the pixels together, that's actually what we saw in terms of the land and ocean trend. So red is the land trend, the blue is ocean trend. What does this one tell us? Sure. So you are talking about why this region got affected more than other region? Is that your question? Okay. Yeah. So remember when we talk about the climate variability itself, different regions naturally they are different. There are some inherent features there. So for example, for polar region, right? So they have a lot of sea ice, seasonal sea ice there, right? So remember for sea ice changes is actually positive change, right? You actually, they are actually most vulnerable to temperature change, melting the sea ice, and they actually, accelerating the change because of albedo change, right? So that's basically why, that's, the inherent feature of that region actually responsible for that. Yeah. Yeah, that's a good question. So, So when we look at this one, the land and the ocean, so what's the major conclusion you can get from this one? Yes, it's not like a tricky question. Really, just try to let you to raise a figure and interpret the results. Can you be louder? I heard somebody talking. Right. So I guess your comments on the difference between land and ocean, right? Yeah. So yes, exactly. So basically, we know both land and ocean, they are actually increasing. The temperature is increasing, right? That's one message we can get. But also, you can say the land temperature increase almost double the ocean, right? So the rate of increase is actually not the same, right? Land warming much faster than ocean, right? So that's because ocean has a much bigger heat, like a buffering capacity, right? So, but ocean definitely is still warming, right? So if your IPCC report has a special chapter just for ocean, talk about ocean heat content, ocean salinity, how things are changing. But in general, we know land and ocean are different. The rate of change are different, right? Land is just warming much faster than the ocean, right? And then if you average this, get a global average of temperature change, right? So that is basically the surface temperature change. And this one is a decadal change. Every 10 years, how things are changing, right? So I guess, all of this are not surprising. We know, like, the Earth's temperature has been increasing, right? So the most warmest years in recent decade, right? So it's becoming warmer and warmer, right? So that's a key message. So, this is when we talk about global warming, right? We really talk about the troposphere, right? So the atmosphere we live in, right? The lower atmosphere. But sometimes we don't talk a lot about stratosphere, right? So that is upper atmosphere trend, right? So that's also in IPCC report. So that's give you the global trend, different stage, but also tropical region in terms of a troposphere. In terms of the stratosphere, right? Again, we talk about stratosphere. That is we are talking about is much higher, right? So that's between 0 and 10. That is we consider troposphere, and above 10 roughly, right? That's a stratosphere, right? Based on this one, this trend, you can look at this as well. But in general, what's your major conclusion for the stratosphere temperature trend? So again, that's the x-axis is temperature trend. You have a 0 and then negative and the positive numbers, and the y-axis is height, right? The altitude. What's a general conclusion you can get? Let's just say, like they all tell us similar story. Let's just talk about the first one then. That's true. As you go up, as temperature decrease, right? But here we are talking about we are talking about the temperature trend. That's a temperature per decade. We are talking about in 40 years how things has been changing. So what kind of major conclusion you can get from this? So the stratosphere temperature is increasing or decreasing? Yeah, you can talk with your neighbors, discuss, and then get it. Remember, we talked about the temporal trend, right? So not the spatial trend. So any question about the figure? How do you read the figure? Okay, I guess for the sake of time, we'll talk about this, right? So, like you guys mentioned, right? If you look at the height profile, sure, yeah, they're always warmer in troposphere and then colder in upper atmosphere, right? So that's kind of the vertical trend. But we are looking at is in the last 40 years also, what is the general trend? You can see for troposphere, right? So that's above zero. That means that's warming, right? Temperature is increasing, right? So when we talk about global warming, we actually talk about the troposphere, right? So that is a layer we talk about, right? But the ones we don't talk about a lot is actually the upper atmosphere, right? About 15 kilometers. You can see it's actually global cooling, right? Stratosphere is cooling, right? So that's because the number is negative, right? So, like in the past, so this one tell you a similar story. Is a kind of a spatial average, right? So you can say, depends on where you are, but in general, like a lower atmosphere is right, is a global warming, right? So if you move up, you can say it's actually cooling, right? The stratosphere is actually has a cooling trend. So, in the past, the climate denier will say, we have a cooling happening, right? Why we say that's global warming, right? So, that can trick people, right? So, but in fact, right, if you, know the meteorology, that's exactly what we expected, right? The cooling trend, right? So because why global warming, right? So because, we have a CO2 and other greenhouse put a layer, right, in our atmosphere, lower atmosphere as a blanket. All the heat actually got trapped here, right? So that's warming us. So because all the heat trapped here, you can imagine, right? So there will be less heat, like here. It becomes slower, like a cooling, right? So that's just the net energy balance, right? So I guess for you, really just try to make sure you understand it, right? So when we talk about global warming, we really talk about the troposphere part, right? So in the stratosphere actually is cooling, right? So that's very interesting, right? So the boundary between troposphere and the stratosphere, roughly is 10 kilometers, but it's not like a uniform everywhere. Somewhere will be a little bit higher, some be a little bit lower, right? But global average is maybe 10 kilometers-ish. But the thing is that there are meteorologists has been studying how this boundary has been changing, right? So their main conclusion is actually IPCC report here didn't talk about this, but in general, what we know is this boundary has been moving up slowly, right? So that's actually, part because of the global warming as a consequence. So what do you think the consequence that will be if the boundary move higher and higher? What do you think that will happen to us in terms of taking airplane? This Nature paper actually specifically talk about this. So basically that means your air ride will be much more bumpier, just because all the weather conditions happen in troposphere, right? If the height becoming higher in the future, because if the plane doesn't change their altitude for flying, that means all weather pattern will become higher and higher. There will be a lot of bumpiness in the flying, right? So that's will be right if an airplane doesn't really keep become higher and higher. So to me, it's just very interesting to think about how climate change could affect many aspects of our life, right? So questions? Okay. So so far we talked about really the kind of the temperature profile, temperature part. So the next few slides we'll talk about water aspect, right? So when we talk about first we talk about the humidity, right? The humidity in the air, right? So as we all know, there are different definitions for humidity, right? So there one definition is a specific humidity, right? So that's by definition really talk about absolute amount of water vapor in the air, right? Either per weight or per volume. That is a specific humidity. And the other type of humidity representation is relative humidity, right? So that's relative humidity is the ratio, basically is the actual amount of water vapor in the air divided by the saturation amount of water vapor in the air, right? So that's why we call it relative humidity. So really, so this one is how much actual water vapor there, and this is in theory under that temperature what's the maximum amount of water vapor the air can hold, right? So that's the ratio we call the relative humidity, right? So the amount of water vapor can hold is you can say based on this equation we know is an exponential equation. That means the higher the temperature, the air temperature, the more water vapor the air can hold, right? So the higher the temperature, exponentially the amount of water vapor the air can hold exponentially increase with air temperature, right? So that's what this equation tells us. So that has a consequence when we talk about the changes in specific humidity and relative humidity. So here is a global trend for the changes in specific humidity, and this is a global average, and this is relative humidity, and this is a spatial distribution. So let's, for now, just forget about the spatial distribution, look at the global average. So what's the general trend here? What is the trend for specific humidity? What's the trend for relative humidity? And why you think that's the case? Let's one step ahead. Let's like a first step. What's the general trend for specific humidity? Increasing or decreasing? Specific humidity. Increasing, right? Yeah. So this one is a specific humidity, right? So that is the absolute amount of water in the air. So you can see that is increasing, right? So different data set basically show you the same trend, right? So that's not surprising, right? So higher temperature, like more evaporation, right? So there are more water vapor in the air, right? So that's why specific humidity is increasing. And how about relative humidity? It's decreasing, right? So there's different data sets at different degree of decreasing, but in general they show like a decreasing trend. Why you think relative humidity is decreasing? data set from UK and GPCC, right? So that's from US. So there are different data set, give you the kind of the rainfall pattern. Depends on how much interpolation they do, right? So some has a higher interpolation than other data set, but in general, that's a global trend, and this is a global average across all the grid cells. So what general trend you'll see in terms of precipitation at a global scale? Let's really just focus on this one. So is it increasing or decreasing? Or no change? Can you say louder? Slightly increase, yeah. So yeah, basically for precipitation, essentially for most of part, right, in the last 100 years, it's not really changed too much. But in recent maybe 20 years, right, slight increase, right? So that is the global average, remember, right? So, precipitation has a lot of regional differences, right? So there are actually some places they have a bigger increase, some places they actually decrease, right? So a lot of people use like a drier part getting drier, wetter part getting wetter, kind of like a description, right? So that's more or less correct, right? So in the wetter climate, their increase is actually bigger, and in drier place they tend to decrease. And then average out overall is a very small increase overall, right? So, but for precipitation, right? Later we'll talk about that, right? So it's not only total amount matters. Sometimes how the precipitation delivered is also matter, the frequency, right? So because right now the general trend is a lot of time when you look at the place, the total amount of water they receive doesn't change, but the storm become bigger. Essentially that means the same amount of water just come like in a couple of big events, right? So that's not good for agriculture, not good for vegetation growth, right? So later, yeah, I will talk about that when we talk about the science part. So that is a kind of a global precipitation trend. Just give you the idea. That's all from IPCC report. Give you the kind of global distributions and also global average. So the last couple of slides, we'll talk about this is a stream flow, right? So essentially what IPCC tell us is they basically have a low confidence in terms of global trend for stream flow, right? So just because some places you have a very dense network for stream flow measurement, like in US, like USGS monitoring very large network for the stream flow measurement. But in many parts of the world, a lot of stream are not gauged, right? So nobody measures their stream flow. So part of the reason for that, part of the reason you don't have a global coverage, and then you have low confidence for the global stream flow. But in general, people find is there are more places they actually show you decreasing trend. But we just have a low confidence because of data scarcity. So that is for the stream flow. Yeah, I have a couple slides for large-scale circulation, but I think we could just stop here. Yeah, I guess. Yeah, if you are interested, we can talk about it later. But like for large-scale circulation, we talk about Hartley cell, like Hartley circulation, and the worker cell, worker circulation, right? So how they are changing, like what we know about them, and how do they impact our climate system. That will be, we kind of run out of time for that. But in general, I want to emphasize one thing is, worker cell, right? So that's actually happened. That's from a British scientist. Is Walker, Dr. Walker, right? So he actually did his field observation in India, right? So actually discovered the worker cell, right? So that's actually very relevant to this continent, to you guys. And also, worker cell is very relevant to El Nino events, right? So if you have a stronger worker cell, that means you have a La Nino events. You have a weaker worker cell, you have a El Nino events. So, but yeah, I guess that's a more like a large-scale circulation. We don't. Yeah, we won't talk about that, but if you are interested, we can talk separately. So, any questions for the content we covered so far? We cover quite a bit of stuff. I just want to make sure you get most of the stuff we talk about. Any questions? You're good? Okay, so yeah, go ahead. So you said the drought has been increasing. Can you repeat your question? Sorry, I don't think I still. Yeah, can you come closer, be louder? Yeah. Polar region, you mean? Yeah. Yes. So yeah. So yeah, I mean it does, right? So you are talking about the polar region. Yeah, the rainfall change there is bigger. It's become more like rainfall there, more flooding there. Whether climate change is responsible for that, right? So yeah, I think so. Yeah, because just more warming, more ice melting, you change the local climate, becoming wetter. Yeah. Right. Arctic, I mean, I think because of the Arctic ice cover, like seasonal changes, it's definitely get affected by the warming as well. Yeah, that's should be very similar to. I mean, the ice is very different. One is a permanent, like in Antarctic is a very thin ice, and the Arctic is very thick ice, right? So, but they are still ice. They melted and they changed the local climate. Yeah, it's quite higher. It's quite thicker, right? Yeah. It's more multi-year sea ice. Antarctic is more like an annual sea ice, right? So yeah, like shallow, sure. Any other questions? Okay, all right. Thank you, guys. I guess we'll take a break, right? So then we'll actually go to the next section about the tutorial. All right. Thank you. No, I don't think it's on. Hello, hello. No, I don't think it. Hello, hello. Is can you hear it? Okay. So should I start? Are you ready? You're ready. Okay. It's good. All right. Okay. Good afternoon again. I'll try to speak slowly, and if you have a trouble like hearing me or understand me, just raise your hands. I'll try to do that slowly. So I don't know. So this will be the tutorial section, right? So the idea is for this particular one, I'm going to talk about the writing, right? So how do we write effectively, like writing scientific papers, right? So I will just talk about different sections and talk about my experience and give you some my personal experience. But if you have questions, feel free to raise your hand and we can talk about it. So can you hear me okay now? Okay, all right. So I guess first I start, so basically talk about, I have a lot of experience writing, right? So, I've been writing many papers, including in the most, I guess, hard journal to publish, right? So I do have a lot of publications myself, and my work was, highly used by other researchers. I talk about in the morning, and also I serve editor for several journals. So for example, I'm the editor-in-chief for Journal of Arid Environments. Right? So that one is a journal specifically deal with any research related to arid environment. Right? It's a multidisciplinary journal. Right? We have hydrology, we have people doing anthropology, we have people doing animal study. Right? So they are very diverse. So some doing remote sensing. Right? So it's a quite diverse range of topics. So I'm the only editor-in-chief. I read every single paper, submit to that journal, right? So, I probably reject 50% of the submission initially, and then after that, I have a 10 editor working with me, right? I send the paper to them, they will handle, right? So I'll be the kind of the the gatekeeper, the first person to read and also make the final decision, right? So, I can share experience. What a terrible paper is, I can easily reject, right? So that's my experience for that. And also, I'm an editor for HYS, right? Hydrology and Earth System of Science, right? So maybe you heard of that. That is EGU journal, right? So it's from European Geophysical Union. So it's specialized for hydrology subject. And also I'm a social editor for journal Hydrology. So probably it's one of the major journals for hydrology field. So I handle some paper for them since I'm super busy. So for this journal, I handle almost 1,000 submissions per year. Like I read every single of them, right? So it's actually a lot of work. So for them, I handle much less. And also I'm a editorial member for scientific data. That is one of the journal belong to nature groups. So this one is specifically published like a data paper, right? If you have a data set you think it's worthwhile for other people to use, you can publish in this journal. It's pretty highly used. I think a pretty high impact factor for this journal. Right. So I guess the point is I do write paper myself, and also I handle others' paper. Right. So I do have a lot of experience reading papers, writing papers. So that's why I think it's good to share you some first-hand experience about writing papers, about reading others' papers. So when we think about the journal article, right? So it's actually to me is compared to a lot of creative writing, right? Write an essay or something, it's actually quite straightforward to write because you have a fixed format, right? For most of journals, you really need to work on the main sections, right? So typically you have a title page that includes the title of the article and then all the authors, other affiliations of the author, right? So typically that's the title page, the first page, and then you have a second page specifically have an abstract, right? So talk about what's a kind of a short summary of your paper, and then you have a introduction section, you have a method section, right? Result section, and then discussion section. Sometimes people combine results and the discussion into one place, especially for the shorter journals, right? So for geophysical research letter, like JRL, right? For like a AGU journal, right? So a lot of people they will combine results and the discussion in one section, just be more efficient in space. And then because sometimes you have a acknowledgement is optional, and then you have a literature section, right? So that's kind of the almost like a fixed format for like most of journals, right? So, and then we know in general what each section should tell you, right? So the abstract really you should have an overview of this paper. Abstract is kind of mini paper, and then you have an introduction talk about why this question you study is important, right? Why is novel, right? So that's the place you try to make the argument for that. And then you have the material method, right? So the method section really, you have to write how exactly you did the thing you did, right? And then the results, you talk about what the major finding you have. And the discussion really, extending the results. After you're reporting the results, you should interpret, right? So what is actually the results means and why that results happen that way, right? So you have to add certain interpretation for the results, and also what are the broader implications of your results, right? So that's a discussion, and then optional ones like acknowledgements, right? So where is your funding source, right? Especially you have external money, you need to put there, right, for writing reports later. And and also maybe your group members helping you out with that project. You need to send them, and then you have a literature section, right? You refer to whatever the previous papers you use in your study, and then a lot of time people use appendix, all called supplementary material, right? Especially for top journals, right? If you write a paper to Nature, right? Your paper may be 5 pages. As a supplementary material, probably 100 pages, right? So that's very common, right? So yeah, so that's depends on the journal, right? Many journals you don't need this, you don't need supplementary information there, right? So that's an option. So I guess that's a kind of the overall the major component for a research paper. So what I'm going to do is I just go to different sections, give you the idea what's needed, and give you some examples and give you some thoughts about different sections. And if you have questions, for different sections, how to write that well, you can ask me, and yeah, I can maybe share further information. So we'll start from beginning. So we'll start from the title part. So I guess for title, really, you need to be specific. Talk about what's the content you try to answer, right? It doesn't have to be a complete sentence. It's really a phrase, really, right? So sometimes the better title, you actually already tell the readers what exactly you found in what the whole paper about. That's I will consider the best title, right? So people read your title, they already know exactly what's your major finding from this paper, right? So for titles, you try to avoid using jargons like the terms only specific to your field, right? Try to use general language everybody can understand, right? So that is the kind of the common practice you should aim at to write your title. And also, for good title, you try to avoid using like how this happened, why this happened, things like that. That's not considered as a good title. Try to avoid using them. So that's basically kind of the general idea about title. So I gave you an example of your course coordinator role, right? So I'm a co-author. So this is a good title, right? So talk about the specific characteristic of a flash dot in India, right? So that's give you the major content of this paper, right? So that is a good title. But like I mentioned, that's you could be better, right? So depends on the subject you are working on, depends on the results. For example, this one I think would be better title. Right, so this one talk about vegetation greening mitigates the impact of increasing extreme rainfall. Right, so this is a paper I'm co-author from a colleague from Indiana University. We'll talk about this paper specifically later on. We'll talk about this I think tomorrow. But I just give you some examples, right? So this one would be, I would say, like a standard title, right? It's good one, right? Give you the key content of the paper, right? So people know what you did, what your major subject of your study. And this one already tell you what the key finding is, right? So basically, you already know what, you don't even need to read abstract. You already know, okay, what the key finding is. So that's good, because sometimes people are lazy, right? So they may not read the full paper, they only read abstract. Some are even lazier, they only read titles, and they already know what your main results is. They can use your results, right? Because as a scientist, when you write your papers, the final goal of your writing paper is not to get published, right? So publish, sure, you want to get published. That's the first step. But the final goal is you should want people to use your paper, to cite your paper. That should be your final goal, right? So whenever you write any sections, you should keep that goal in mind, right? Why I should write a certain way? Because it will make the reader easier to actually digest the information, to actually to use your paper, use your funding, right? So that will be your final goal. I guess just keep that in mind. Yeah, again, feel free to stop me anytime, right? So I will have a short lecture, and then there will be a quick exercise later in the end. So that's a title page, right? Should be straightforward, right? And then title page also typically include authors, right? So of course author really, who contribute to the work, right? So really, you can think like typically the person who wrote the paper should be the first author, right? So that's the typical role. But all authors should make significant contribution, right? So you can't, find the people to be author just because these people is your advisor. If the people didn't contribute anything, they shouldn't, right? So there are ethic issues, right? So when we think about the guideline, right? So there are different societies, different journals have their guidelines in terms of who should be on the author list. So that's guideline from Nature Group. So they will talk about what their expectations for authorship for authors. Right? So the idea is, each author should make a significant contribution. So the contribution could come from different aspects. So the contribution could maybe help you conceptualize the work, design the work, right? So that's contribution. Or could maybe your fellow graduate student help you get the data, or help you with the data analysis in the lab, or just doing the statistic analysis, help you for that, or create some new program softwares to help you analyze the data. So. And also maybe someone help you edit the paper intensively, help you to polish, to extend, to improve the paper. So they have to make some important contribution for one of these areas. So that's one of the requirement. So really the contribution part. And also the second part is when you submit a paper in theory, all the authors should approve the final version. They should all agree, okay, that is the final version we will submit, right? So because sometimes that happens, people submit a paper and the co-author said, my concern wasn't addressed yet. I'm not proving the final version. That's occasionally that happens. So that will be author dispute. And also the third part is really, the first part is kind of the credit part, because we know authorship is good. You want to publish more papers, you want to co-author more papers. That's a credit, right? So that's a good thing. So the third part is really the responsibility part. So when you grade on a co-authorship for a paper, really you also take the responsibility, right? If you are co-author to a research paper, right, you are not only responsible for the credit, you're also responsible for if the paper, for example, gets retracted, that's your problem too, right? So even you said, okay, I only work on this section, and the problem section is that section, it's not my problem. But basically the expectation in scientific world is, if you are co-author on that paper, regardless the section you work on, you guys are on a team. You grade, you sign on for that. If there are blames, you need to take the blame too, right? Besides credit. But of course, there's small chances, like scientific misconduct or things like that. But you need to pay attention. Authorship not only carry credit, it also carry responsibility, right? So, does happen. As editor, I know, for example. Somebody proposed a special issue, right? So, as an editor, I just approved the kind of the science content, and then there will be people publisher above me, they will actually look at all the guest editors' profile. They will actually check whether they have a misconduct or some plagiarism or something like a on record. If they are, they will tell me, don't prove the special issue, things like that. So it does happen in the past. So that's if you co-author a paper that has issue, right? So it's actually affect you in the long term. So that's why be careful about authorship. Yeah. So that's not only credit, there are other purposes as well. So after title and authorship, right? So the next part will be abstract, right? So abstract to me is really a mini paper, right? So abstract, you should have almost everything about that paper, right? First sentence will basically the background of your study, right? Why I study this, why this is important, and then the second sentence, first sentence the background, and then second you'll probably talk about what's the knowledge gap of this field, and then you'll talk about what I did, the method, and then what your finding is, and then talk about the implication or interpretation of that finding. Right? So abstract is almost like a mini paper. Right? So that is a good abstract. Right? So depends on the journal you are submitting. Right? So some require very short, like abstract. Some could be longer. Right? So it's a big range in terms of how long that one is. So I just give you don't have to read, but that's essentially the abstract from the flooding paper I mentioned earlier. So essentially you can look at you first talk about what the background of the study, and then you talk, however, typically talk about what's the knowledge gap already there, right? And then you talk about what you did to try to address that knowledge gap, and then you talk about what's the results you found, and then you talk about the implications, right? What's the implication of the results, right? So a lot of journals right now, they give you the option to write a plain language summary, right? So especially AGU journals, right? So they almost require, I think, for many journals, you have to write something, for general audience, right? So keep that in mind. So some journals, it's a requirement. But the idea is you not only want your paper published, right? You actually want people to use your paper, right? So this one will be actually a very good way to convince people not in your field to still think, okay, that is a useful study, that is a good study. So make sure you have this mentally prepared. So that's abstract, right? So yeah, any questions, comments? Okay. So yeah, again, I just follow the section. We just talk about the different sections, what general expectations you should think about, and what are the good practice you should pay attention to. So, and then the next section is the introduction section. I put a comment there. To me, I think the difficult section to write, one is the introduction section, one is the discussion section, right? So I typically ask my student, that's two sections, they should pay more attention, also spend more time on that section, right? So for the introduction section, you need to basically provide a lot of information. For example, what the major question of your study is, right? Why it's interesting, why it's important. And also, you should give a very brief literature review of this subject, right? So essentially, you tell people you know what you are talking about, right? You already did your research for this subject. You already know what has been done and what's still not new and what not known, right? That's why you will do this study, right? So you have to have that literature review part. And then, typically last bit of the introduction, people will talk about specifically in this paper what my goal is, right? So you have 1, 2, 3 goals. That's kind of most common way people write introduction. And in terms of the structure, the introduction, people tend to think, that's a kind of inverted triangle, right? So the idea is you start from a bigger picture, right? So what's the general, why this field is important, what's the general field, and then you go into specifics slowly, right? So you narrow down to the specific of your particular field, and then talk about what not known, what need to be done, right? So that's a kind of a general structure, a good structure for introduction. So I guess, the idea is introduction, why is harder? Because you need preparations in terms of literature collection. You need to read a lot of papers. You need to know what has been done, what has been known, right? So because if the stuff you are doing already done, right? So there's no point you do that. You have to have some novel aspect, right? The novelty could be small, could be big, right? So, but it has to be novel in some, to a certain degree, right? So you have to have the novelty, right? So the big novelty you can publish in Nature, in Science. Smaller advance you can publish in disciplinary journals, right? So, but you have to emphasize that novelty. And how you prove that novelty, right? So that's basically, you have to have a literature review to show people, I already done my homework, I know what has been done, and my research is actually new in that aspect, right? You have to clearly mention that. So, as editor, right? So like I mentioned, 50% of the paper I would reject for the journal I'm handling, right? So, novelty is one of the things, if you don't make that clear, that's a easy one to reject. Just say there's nothing new in this, people already know, right? So, you basically need to emphasize that yourself. You have to make that clear. Any questions, comments about the introduction section? Okay. So again, that's need read a lot of reading, right? So to be able to write well about the introduction section. And the next section, typically we write is a material and the method section. So this section and the result section are the two sections I consider easy one, right? So I will ask my students to start writing them, especially for the inexperienced student, like when they just started, I will suggest them writing these two sections first, material and method and the results, right? So the reason for this is, this section you really talk about something you already done, you know what you did, right? So really you try to find a good logic, either like maybe the material you use, the study region you have, and then what data set you use, what the statistic method you use, whatever the logic you found, you follow that. And then you can just write what you did for different sections, right? So a lot of time we use subsections, right? So because again, like mentioned, you could have a study region, you describe the climate, the geography, right? And then you have a data set section where you collect all the data set, right? What's the resolution? How do you, downscaling of, harmonize the data, things like that. And then what's the analysis you did? What kind of how do you calculate certain parameters, things like that. So you typically need several subsections to put them into different sections. So typically you don't want to put any results in this section, right? So only if the results is validate a certain method, you can mention, I use this method and I compare this method with the previous method is still good. Like from only the results specifically related to the method you put there. Very rare you put results in this section. So because it's already been done, right? So typically you should use past tense for method section, right? Because everything already been done, right? So this one again, I would say like the most straightforward ones. So if you just start writing your paper, right? So try to start from this, right? You always start from easier one and then deal with the harder ones later. So that's the method section. And then typically after that, you will have your results section. So again, I will consider this will be easier ones to write as well. So result section, essentially you present your key findings, your key results. So of course, most of the time we'll use graphs, we use figures, we use tables to facilitate the reporting of the results. So a common mistake is that people tend to try to interpret the results in results section. But that's actually discussion material. You don't really discuss results. You just report A is larger than B. Like A is correlated to B, things like that. You don't need to explain why A is larger than B, why A is correlated to B, right? So there's no need to write that in the results section, right? And also, like results section similar, right? Because you have a different part. A lot of time people use subsections to organize results, more logic order, right? So the most common way people use results is also past tense, right? Because results has been done, right? That's what you already found. You use past tense. So that's different from discussion section. Discussion section, because you already talk about whatever already there. You can use present tense, right? So that's a major difference in terms of tense. So again, results really to me should be straightforward to write, right? So especially you are doing something, you produce a figure, right? You already know, okay, that's kind of the results I'm going to present, right? You can already start like writing that, right? So yeah, I think that's this section, the method section should be the ones you start as soon as possible, right? So because for method, when you're doing things, you already know what you did, right? You can start recording what you did later, just put them together and put them in more organized way, in more logic way, right? So these two sections are relatively straightforward to write. So I guess some common issue you try to avoid, right? So for example, sometimes when people write results, they write very tedious ones, right? So they actually talk about every single numbers in the figure, every single numbers in the table, right? So like have a very long paragraphs. That's not recommended, right? So because the purpose for results is summarize the key finding, right? So the figure already there, right? You can say, A is larger than B. You don't have to say A is 10, B is 8. So that's why A is larger than B, right? So because the figure already tell you the number there, right? You don't have to repeat that, right? So that's a common mistake, kind of being tedious, being redundant, try to avoid that. And also, in the beginning of your writing, some people maybe have the same data. You present both figure and the tables. You present in both ways. That's highly discouraged, right? So because they are the same results, you have to decide you use either figure or table. You don't want to present them twice, right? So yeah, don't try to use the same data, present different ways. So yeah, I mean this is basically the same idea as a figure and a table. Try to, when you report your results, try to summarize the results first and report that way. That will be much better than just report every single numbers, very tedious ways. Try to talk about means, percentage rather than raw values. So I guess here just some common issues for the beginners. Maybe if you already have a lot of experience, that's not an issue, but just keep that in mind. So typically the last major section to write after results, that will be the discussion section, right? So again, I will consider this one would be a hard one, right? Probably the hardest section to write out of the whole paper, right? So the purpose for this section, right? After you report your results, you essentially have to explain, right, why that happens, why is your results the way they are, right? So that's the purpose of a discussion, right? But a good discussion, besides explain what the results are, you also want to put the results in a bigger context, right? What the results actually relevant to other people's funding, right? How that help interpret certain things or explain certain things for others, right? So, that's why results discussion section also require you have a lot of the accumulation of literature knowledge, right? Who did this, and what I did, what my results, how my result relevant to others, right? So you need to have some concrete evidence for that to report, right? So that is kind of the purpose. Like a lot of the newer journals, they require you to report the limitation section, right? Or study constraints, something like that. Especially for, I think, Nature Communications, that's required. I forgot. I think Science Advance also required. So they're like top journals. They really pay attention to that. They actually, you have to have this section, right? So you have to write the limitation yourself. You have to be transparent to readers about your major constraints of this study, right? But not all the journals require that. But it is a general good practice to actually have that even for regular journals, right? So that's help you to kind of convince reviewer you actually think about certain limitations yourself, but that's the best you can do. It's still valuable, right? So give people the idea you already try your best for that. It's actually help you, right? So I would encourage you to think about that. Like actually write that on your own and in your discussion section. So discussion similarly, typically you have multiple sections for discussion section, and like we mentioned, because right now you already discussed current results now. So commonly people actually use the present sense. You don't have to use past sense in discussion section. So that's kind of the common way people does. So that's kind of the major component for a research paper, right? So I can just give you some comments for different sections. Any questions? Any doubts like you have about certain sections before we go on? Okay. And then a lot of time, right? So people has a conclusion section or summary section, right? So that's I put an optional there, right? So not every paper has that. It's not required for any journals. But it's a good way to have it because after people reading the long discussion, you want to remind them what really the main results is, what the key finding is. So again, you want to help reader to understand your paper better, to use your paper. Right? So it's good to have a conclusion or summary section for any paper. Right? So I would encourage you to have that. So, but typically you don't want to add new information there. So everything should be already talked about. So it should be a summary of the existing reporting already. Right? So don't report anything new there. And try to. So you can say that there are some similarity between abstract and the conclusion, right? So you can't avoid them. There must be some overlap, especially the key results, right? So that's the things you want to talk about, but try to not make them exactly the same or like almost same, right? So that's won't help you, right? So basically, the editor will maybe ask you to remove one of other. I mean, likely the conclusion section, right? Because abstract is required. So I guess that's just a common sense for conclusion. I think it's always good to have one, but repeat, like a abstract. And then like optional sections would be basically the acknowledgements, right? So who actually help you, who gave you funding, right? So that's optional, right? So not every paper have that, and also the last one will be reference section, literature cited section. Yeah, just this one, just make sure is format consistent, but also is matching the paper you are submitting, right? So every journal has their own requirement, right? So make sure you meet that requirement, right? So, and for the newer journals or there are new requirement. A lot of time people require you to write a data availability statement, right? For all the nature journals, you have to have this. And the AGU journals, you have to this as well, right? So you basically have to report where you store your data, and how give the link. You have to make sure your data is public available, right? So that's many journals try to push that direction, right? So elsewhere journals they don't yet, but you have to write, say, I'm available to share the data if other people request. You have to write something like that, but not like a detailed information. So, and then again, depends on the journals. A lot of time people will have supplementary materials or called appendix. You just give you could be additional text. Sometimes because of the journal constraint, either method section or some other section is very short. You have to report your method in more detail. That's called supplementary text, right? So that could be part of the supplementary material. But more commonly, you have a supplementary tables or supplementary figures, and they are the ones actually showing the results. You use them to back up your conclusion or back up your method, right? So you use them. Just make your argument stronger. Questions so far? Okay. And then last bit will be tables and figures, right? So I guess the rule of thumb is for tables you put the table title on the top, right? So and also for figures and the tables they should stand alone, right? So you should explain all the acronyms in a table, like AI, right? You should say already index, not Air India, right? So things like that. So you just have to explain them every time you use them. Even like table 2, use that again. You should explain again, right? So because the idea is every table, every figure should stand alone. You don't have to use this table to understand this table. Everything should stand alone. And same for figures, right? But for figures, the legend or figure title should be at the bottom, right? So that's a common convention, right? So if you don't do that, people may think you don't know the convention. That's not good, right? So table title on the top, figure title at the bottom, right? So, but again, you want to explain all the acronyms in your figure, right? So even the different figure use same acronym, you want to explain them again and again. Even there take some space, but that's actually help the readers to directly understand the figure. So that's the kind of the major component for a research paper, right? So how different sections works, what my experience, my comments about different section, and last bit, what I'm going to talk about is, how do you make your writing stick, right? How do you write, when you write proposals or when you write papers, how do you organize your writing in a way like people can naturally understand, right? So there are actually ways to do that, right? So I will show you a video. So he's a former professor in the university, and then I think he started like making like a script, helping people write. That's it come up the idea like and but therefore structure. And so, how do you use that structure to make your writing more impactful? So hopefully that works. I will show this video, and then I will show you example I wrote in terms of and but therefore. That's a structure. And but therefore, you think about that structure. For any writing you have, you should think about that. Even for presentations, you should think about that structure. And then last bit, we'll have an exercise using that structure, write something about your research. So let's see whether this one will play. I don't have an internet. It seems to be working.
Storytelling.
Do you know what will happen if you read one book every week?
I try to make the sound a little bit bigger. So, let's see.
Storytelling.
Can you guys hear it? That's too small, too low. Sir, this one. I just try to say.
But you can all use a little help from time to time.
Oh, maybe let's try this one. Plug in.
Therefore,
This one is on.
प्ले करिए वहाँ से प्ले बेस है सर हाँ आ रहा है हाँ उसमें आवाज़ आएगी तो आने लगेगा इसमें अभी वो बोल नहीं रहा है ना बोलेंगे तो आएगी
but you can all use a little help from time to time in our storytelling skills. Therefore,
इसको लगाइए ना
we're going to be offering a few tips in this talk. And this is the first one. We call it the and, but, therefore template.
उसके पीछे
I'll get to it in a few minutes. But I want
हाँ आएगी हाँ आने लगी
That's the biggest. Maybe here, that sound here too. Volume.
storytelling and
Yeah, it is.
but
That's already biggest. That's already highest. Can you guys hear it? Okay. I guess.
You can also turn on the subtitles so that subtitles
Let's see.
in settings there. Yeah, that's speaker वहाँ पे sound
I can't do both. I mean, yeah, I think it's not loud enough, but maybe you can move closer. Let's see. Let's try it.
storytelling is universal.
this one doesn't really do. Okay. Okay, that's low.
But we all use a little help from time to time in our storytelling skills. Therefore, and this is the first one. We call it the and but therefore template. I'll get to it in a few minutes, but I want to begin with a simple question, which is, how much time do you need to tell a story? Could you tell a story in 20 minutes? Could you do it in 30 seconds? Could you do it in 10 seconds? Could you tell a story in just 5 seconds? A few years ago, a website appeared called 5-Second Films, and I'm showing you one of the films right now. And as you watch it, ask yourself, does this tell a story?
Maybe I'll start again. Sorry. Since
Storytelling is universal. But we can all use a little help from time to time in our storytelling skills. Therefore,
Yeah, sorry, the sound
piece
wasn't.
of advice that's been going around in recent years, which is that we all
Background is still playing. So yeah, sorry, the sound wasn't loud enough, but hopefully you'll hear the kind of using subtitle guides in science, right? So the idea is for good writing in general, could be scientific writing, could be the writing movie scripts, right? It's the same idea. You actually try to tell a story, right? So if you can write a story, it doesn't have to be long or short. If you can write a story that will stick, right? So you want your reader to read your paper or your proposal as a story, right? So what's the key for writing story, as a speaker talk about, is really the and but therefore structure, right? So you talk about something and then and something like a and but that's maybe the knowledge gap, things like that, and then therefore you want to do something, right? So that's apply proposals, apply to journal articles, anything you write, you want to use this structure, right? So even for presentation, like the speaker mentioned, right? When you go to a conference, give a presentation, you need to talk about background, right? And the background, but we still don't know this, therefore I did this, right? So that structure can also apply for presentation setting as well, right? So I guess really the key thing is make sure you have this type of structure in any paragraph you write, so that will be easy for people to get the picture as a story, right? So this is a proposal actually I wrote, is I think it's a project summary part. Let's give you example. I'll maybe let you read first, and then we'll do an exercise like yourself using this structure. Write something, right? It could be a current project you are working on, but it could be a proposal you try to write, or could be some results you already got. So try to use and but therefore structure. Try to write that way. So that will be just more effective, more sticky to readers. But first I let you to read this one first. So I guess this one just try to set up examples how this one used in real world, right? So actually when I wrote this proposal at that time, I didn't realize I used this structure, right? So that's kind of afterthought. I realized that's actually a good way to write this way, right? So I guess but if you writing intentionally, that's more effective, right? So I start like pay attention to that and try to write things as a storytelling, right? So I guess so that's how you do that. And this is a proposal, and I think Thursday my talk is actually about this. Just give you a preview for this topic. So and last, really just let's try to do an exercise, maybe 15 minutes, and try to write something yourself. Use the and, but, therefore structure, right? So it could be a proposal, could be a results you have. Could be applied to any type of writing. But you can think about yourself and then start writing something, and then you can share with the neighbor, and you discuss what read each other's work and give each other ideas. But you can also talk with me as well. So that will be the exercise. So any questions so far? Yeah. I mean, introduction discussion will probably be most powerful ones. Research gap. in terms of a writing of research gap, or how do you actually identify research gap? I mean, which one? Identify research gap, or how do you actually write about the research gap? So that's the kind of inverted triangle thing. Like, you start from a broader field, for example, how climate change will impact the compound, drought and extreme events, right? You can start from the background, say, climate change is happening, is everywhere, right? Is accelerating, right? Whatever the background is, and then you talk about, the potentially, like there are compound events already happening, and climate change should affect the compound events, but we don't know exactly what the degree and how exactly affect. Like a kind of a bigger and then funnel down to the kind of smaller version. So, but to write well is really, that's why I said it's harder, because you have to justify every sentence based on literature. Whatever you said, you have to have a support for that. This has been found, but we don't know this, and that's why I study this, things like that. So structure-wise, it's kind of a funnel type of a structure, but you have to use solid literature to support, the structure. Like I say, this general picture, and then narrow down, and then talk about that's a knowledge gap. Yeah, is that? Okay, sure. Any other comments, questions? Yeah, but again, introduction is a hard one, right? So it's to be able to write well, you have to read a lot besides the techniques. But that means their techniques make you write more effectively, like more storytelling. But it's not all, right? You still need to have a collection of literature. So I guess, let's use minutes, 15 minutes. Everybody write something, and based on your research, and then you talk with your neighbors, and try to help each other, see whether you reach the goal, and but therefore structure, and whether people can easily get what you try to describe. So let's use next maybe 15 minutes. Everybody write something. You can use your computer to type, or you can use handwriting. Doesn't matter. How do you write? So questions about what to write. Really think about your research subject, the ones you try to study, and put that into and but therefore structure. Say that again. You can just write like one paragraph. So you can use computer, but you can just write. Yeah. So, hello, can you hear me? Okay. So yeah, I think that's pretty much we are almost time now. Any questions for the structure we talked about? So like I mentioned, like in general, right, like and but therefore the structure could be used for like any scientific writing you use, either research papers or research proposals. It's just a powerful way to organize your story. Right? So hopefully you practice more and more, very familiar with the structure. It's just an effective way to do that. So and also for in general, the scientific writing, right, for different sections, some of you just started writing your own, right? Some already write many papers. But if you have questions, comments about certain things, just come to me. We can talk about it. Right? So yeah, I guess that's pretty much for this tutorial. Right? So we will continue tomorrow to start talking about specific topics of research. A lot of